Imagine looking up at the night sky and realizing that the universe isn't just made up of scattered stars and galaxies floating alone in the void. Instead, there are places where entire galaxies are crammed together, locked in a gravitational dance that has been going on for billions of years. Some of these groups are so tightly packed that they defy everything we thought we knew about galaxy formation. One of the most famous of these is Stephan's Quintet, a collection of galaxies so close together that they're literally ripping each other apart. But here's the strange part: these compact galaxy groups shouldn't even exist, at least not for long. The immense gravitational forces between them should either fling them apart, or merge them into one giant galaxy relatively quickly on a cosmic timescale. Yet, we see them all over the universe. How is that possible? Why do they exist at all? And more importantly, what do they tell us about the past and future of the universe itself? To understand the mystery of compact galaxy groups, we first need to grasp what makes them so unique. Most galaxies exist in larger clusters, spread out over millions of light years. The Milky Way, for example, is part of the local group, which includes Andromeda and about 50 other galaxies. But our neighborhood is relatively spacious. Compact galaxy groups, on the other hand, squeeze multiple galaxies into a space that could easily fit inside the local group. These galaxies interact constantly, exchanging gas, distorting each other's shapes, and even colliding. The sheer density of these groups leads to some of the most extreme galactic interactions in the universe. In Stephan's Quintet, for example, shock waves from these interactions heat up the gas between galaxies to millions of degrees, making it glow in X-rays. It's a chaotic, violent environment where galaxies are reshaped, their gas is stripped away, and entire new stars are formed at an accelerated rate. One of the biggest questions surrounding compact galaxy groups is how they formed in the first place. The standard model of galaxy formation suggests that galaxies grow by merging and accreting smaller galaxies over time. But in the case of compact groups, we often see galaxies of similar size and mass interacting as if they've been together for a long time. This suggests that they may have formed together from the same primordial cloud of gas and dark matter. Alternatively, some of these groups may have been brought together by gravitational interactions, pulling them into a shared orbit before their eventual merger. But even if we understand how they formed, that still leaves another big question: how do they survive for so long? Simulations suggest that the galaxies in these groups should merge within a few 100 million years, an instant on cosmic timescales. Yet, we observe many compact groups that appear to have been around for billions of years. This has led some astronomers to propose that these groups are continually replenished, with new galaxies being captured by their gravitational pull even as others merge or are ejected. There's also another strange aspect of compact galaxy groups. Some of them appear to be missing large amounts of dark matter. Dark matter is thought to be a crucial ingredient in galaxy formation, holding galaxies together and influencing their motion. Yet, in some compact groups, the way galaxies move suggests that there's far less dark matter than expected. This has led to theories that these groups might have formed in an unusual way, or that interactions between galaxies have somehow stripped away their dark matter over time. And then there's the question of what happens to these groups in the future. Will they eventually merge into a single, giant elliptical galaxy? Will they be torn apart by interactions with other galaxies outside their group? Or is there something about these systems that allows them to persist far longer than we expect? Stephan's Quintet, in particular, has given us a unique window into these mysteries. Located about 290 million light-years away, this group consists of 5 galaxies, but strangely, one of them isn't actually part of the group at all. The 5th galaxy, NGC 7320, is much closer to us than the others. It just happens to be in the same line of sight. The remaining 4 galaxies, however, are locked in a gravitational struggle that has been ongoing for hundreds of millions of years. Observations of Stephan's Quintet have revealed enormous shock waves generated by galaxy collisions, heating gas to millions of degrees and producing intense X-ray radiation. These shocks are some of the largest ever observed in the universe, giving us insight into how energy is transferred during galactic interactions. The group has also been a testing ground for theories about how galaxies evolve, as the interactions between these galaxies strip away gas and trigger bursts of star formation. Beyond Stephan's quintet, other compact groups show similarly extreme behaviors. Some have large streams of stars and gas stretching between galaxies, evidence of past interactions. Others appear to be in the early stages of merging, with galaxies slowly being pulled together by gravity. The study of these groups has also provided clues about how galaxies in the early universe might have formed and evolved. One particularly intriguing idea is that compact groups might be the missing link between loose galaxy clusters and fully merged galaxies. In other words, they represent an intermediate stage in galaxy evolution, a step between isolated galaxies and giant elliptical galaxies formed through repeated mergers. If this is true, studying compact groups could give us a clearer picture of how galaxies evolve over billions of years. Another fascinating aspect of compact galaxy groups is their potential role in shaping the large-scale structure of the universe. When galaxies interact in these dense environments, they lose gas, and their star formation slows down over time. This means that compact groups could play a crucial role in regulating star formation across the universe. If compact groups are common, they might be an important factor in explaining why the universe isn't filled with an even higher number of bright, star-forming galaxies. And then there's the role of supermassive black holes. Almost every large galaxy has a supermassive black hole at its center, and when galaxies merge, these black holes also merge, releasing enormous amounts of energy in the form of gravitational waves. Studying compact galaxy groups could help us understand how these black holes interact and grow, shedding light on one of the most mysterious aspects of galaxy evolution. Despite everything we've learned about compact galaxy groups, many questions remain unanswered. Why do some groups seem to persist for billions of years while others merge relatively quickly? What role does dark matter play in their formation and evolution? And could studying these groups help us understand the fate of our own galaxy, the Milky Way? What we do know is that compact galaxy groups represent some of the most extreme environments in the universe, where galaxies collide, merge, and transform in ways that challenge our understanding of cosmic evolution. Every new observation adds another piece to the puzzle, bringing us closer to unraveling the mystery of these fascinating galactic structures. The more we study compact galaxy groups, the more we realize how much they challenge our understanding of the universe. Their existence alone raises questions about how galaxies form, evolve, and interact on cosmic scales. But beyond their sheer strangeness, these groups also offer a glimpse into the larger forces that shape the universe itself. By studying them, we're not just learning about a handful of unusual galaxies, we're uncovering fundamental truths about how matter behaves in deep space. One of the biggest puzzles about compact galaxy groups is the way they disrupt our models of galaxy interactions. When two galaxies collide, the immense gravitational forces pull at their stars, gas, and dust, creating long tidal tails that stretch across space. This process is well documented in many interacting galaxies. However, in compact groups, the sheer number of galaxies in close proximity means that these interactions happen on an entirely different level. Instead of a simple two-way merger, you have a chaotic system where multiple galaxies are constantly pulling at each other, creating a turbulent environment where traditional models start to break down. Take Stephan's quintet as an example. This group isn't just a static collection of galaxies, it's a battlefield. The galaxies are slamming into each other at speeds of hundreds of kilometers per second, creating massive shock waves that compress gas and trigger bursts of star formation. This constant turbulence also leads to the stripping of gas from galaxies, a process that can eventually leave them barren, preventing further star formation. In some cases, the stripped gas doesn't just disappear, it collects in intergalactic space, forming massive clouds of hot plasma that glow in X-rays. These intergalactic shock waves are some of the largest ever observed, providing a rare look at how energy is transferred in space. What's even more fascinating is that these interactions don't just affect individual galaxies, they reshape the entire structure of the group itself. As galaxies pass by each other, they can steal material, altering their shapes and compositions. Some galaxies get stretched and distorted, forming long, twisted arms of stars and gas. Others get completely cannibalized, merging with larger galaxies to form something entirely new. Over time, these groups may evolve into a single giant galaxy, a process that might even explain the formation of some of the largest elliptical galaxies we see today. But if compact galaxy groups are destined to merge, why do we still see so many of them? That's where things get even more puzzling. Astronomers originally thought that compact groups should be relatively short-lived, merging into larger galaxies over a few 100 million years. Yet, we continue to find them scattered throughout the universe, some of them appearing to have existed for billions of years. This suggests that either the process of merging takes much longer than expected or that new galaxies are constantly being pulled into these groups, keeping them active. One way to study this question is by looking at the distribution of dark matter within these groups. Dark matter is thought to make up about 85% of the universe's mass, influencing the way galaxies move and interact. In most galaxy groups and clusters, dark matter acts as an invisible glue, holding everything together. But in some compact groups, we see something unusual: galaxies moving in ways that suggest there's far less dark matter than expected. This has led to several intriguing theories. One possibility is that the intense interactions within compact groups somehow strip away dark matter, leaving behind galaxies that behave differently from what we would normally expect. Another idea is that some compact groups formed in an entirely different way from typical galaxy clusters, perhaps emerging from a different kind of cosmic structure. Another major mystery surrounding compact galaxy groups is their impact on star formation. We know that when galaxies interact, their gas clouds get compressed, triggering new stars to form. In some cases, this leads to spectacular bursts of star formation, where entire regions of space light up with new stars. But in other cases, the opposite happens. Interactions strip away gas, shutting down star formation and leaving behind dead galaxies that no longer produce new stars. In Stephan's Quintet, we see both of these processes happening at once. Some regions are undergoing intense starbursts, while others have been stripped of gas entirely. This makes it an ideal laboratory for understanding the life cycle of galaxies and how they transform over time. The presence of supermassive black holes in these galaxies adds another layer of complexity. When galaxies collide, their central black holes can be fed with new material, triggering powerful jets and outbursts that further shape their surroundings. The study of compact galaxy groups doesn't just help us understand individual galaxies. It also gives us insight into the larger structure of the universe. The way galaxies cluster together and interact plays a crucial role in shaping cosmic evolution. Compact groups may represent a key transitional phase, bridging the gap between isolated galaxies and massive clusters. By studying them, we can learn more about how galaxies grow and change, and perhaps even gain clues about the future of our own galaxy. And that's where things get even more personal. The Milky Way itself is currently on a collision course with the Andromeda Galaxy, with the two expected to merge in about 4.5 billion years. When that happens, our galaxy will undergo the same kind of violent interactions seen in compact groups, reshaping the night sky in ways we can barely imagine. Studying compact groups today might give us a glimpse into our own future, a future where the familiar spiral arms of the Milky Way are stretched, twisted, and eventually consumed in a massive galactic merger. But there's still so much we don't know. How do some compact groups manage to survive for billions of years without merging? What role does dark matter play in their evolution? And could these groups help us unlock new secrets about the universe itself? Every new observation brings us closer to answering these questions. Advanced telescopes like the James Webb Space Telescope are now giving us an even deeper look into these systems, revealing details we've never seen before. As we continue to study compact galaxy groups, we may uncover new clues about the nature of dark matter, the history of galaxy formation, and even the fate of our own cosmic neighborhood. One thing is certain: these groups are among the most extreme environments in the universe, where galaxies are torn apart and reborn in a never-ending cycle of destruction and creation. They challenge our understanding of cosmic evolution, forcing us to rethink what we thought we knew about how galaxies interact. And as we peer deeper into the universe, we may find that compact galaxy groups hold some of the biggest secrets of all. The deeper we look into compact galaxy groups, the more we realize that they aren't just a side note in cosmic evolution. They could be one of the main drivers of galaxy transformation throughout the universe. Every single galaxy in these groups is engaged in a delicate dance of gravity, a chaotic yet structured interaction that can span billions of years. And because of their compact nature, these interactions don't just happen occasionally, they are constant, ongoing, and reshaping the galaxies in ways we are still trying to understand. One of the most surprising things astronomers have discovered about these groups is that they often contain a much higher concentration of active galactic nuclei, AGNs, compared to isolated galaxies. AGNs are the extremely bright and energetic regions at the centers of galaxies, powered by supermassive black holes that are actively consuming gas and dust. The gravitational forces in compact groups frequently funnel material toward the centers of galaxies, feeding these black holes and triggering massive outbursts of energy. This means that many compact groups are home to quasars, blazars, and other extreme cosmic phenomena, making them some of the most dynamic environments in the universe. But what's truly fascinating is how these interactions can determine the fate of galaxies. When galaxies merge, their central black holes often end up colliding as well, forming even larger black holes that continue to grow over time. This process could explain why some of the most massive black holes we've ever observed exist in the centers of galaxies that were likely once part of compact groups. In some cases, these mergers can even lead to the ejection of a black hole from its host galaxy, sending it hurtling through space at incredible speeds, a phenomenon that has been observed in some systems. Another major mystery surrounding compact galaxy groups is the presence of ultra-diffuse galaxies, UDGs. These are galaxies that appear to be ghostly, with very few stars spread out over an unusually large area. In many cases, these galaxies contain as much dark matter as the Milky Way but only a tiny fraction of its stars, making them some of the strangest objects in the universe. Some researchers believe that UDGs could be the remnants of galaxies that were once part of compact groups but were stripped of their material by repeated interactions, leaving behind only a skeletal structure of stars and dark matter. Others suggest that they could be failed galaxies, objects that had enough dark matter to form but never accumulated enough gas to create large numbers of stars. Studying compact groups also helps us understand how large-scale cosmic structures form. Galaxies are not randomly scattered across the universe. They are arranged in vast networks of filaments, clusters, and voids, creating a cosmic web that stretches across billions of light years. Compact groups may serve as the building blocks of these larger structures, merging over time to form the massive galaxy clusters we see today. Some researchers even speculate that compact groups might be the remnants of early galactic structures that formed soon after the Big Bang, giving us a direct link to the earliest days of the universe. Another key question is why compact galaxy groups appear to be more common in certain regions of the universe than others. Some areas of space are filled with these tight-knit groups, while others are almost entirely devoid of them. This uneven distribution suggests that the conditions required for these groups to form are not universal, meaning that something specific about their environment allows them to exist. It could be related to the density of dark matter, the amount of intergalactic gas available, or even the influence of cosmic expansion itself. And speaking of cosmic expansion, there's another mystery related to compact groups. How do they fit into our understanding of the accelerating universe? We know that the universe is expanding at an ever-increasing rate, driven by the mysterious force known as dark energy. This expansion should, in theory, be pulling galaxies apart over time. Yet compact galaxy groups remain tightly bound together, seemingly resisting this cosmic stretching. Does this mean that these groups are sitting in special regions of the universe where dark energy has less of an effect? Or are the gravitational interactions between galaxies so strong that they can overcome the pull of expansion, at least on small scales? One way to explore this question is to study compact groups at different points in cosmic history. Thanks to powerful telescopes, we can now observe these groups as they existed billions of years ago, allowing us to track how they have changed over time. If compact groups were more common in the past and are slowly merging into larger galaxies, this could give us a timeline for how galaxies evolve in different environments. On the other hand, if we find that compact groups have remained relatively stable for billions of years, this could challenge our understanding of how galaxies interact on cosmic scales. Even more intriguing is the role that compact groups might play in cosmic recycling. When galaxies interact, they often throw massive amounts of gas and dust into intergalactic space. Some of this material eventually falls back into the galaxies, fueling new bursts of star formation. But some of it may escape entirely, spreading throughout the cosmos and enriching the intergalactic medium with heavy elements. This process helps distribute the building blocks of planets, stars, and even life itself across the universe. In a way, compact groups might not just be sites of galactic destruction, they might also be key contributors to the creation of new celestial objects in ways we are only beginning to understand. The complexity of these groups makes them an exciting field of study, but it also presents major challenges. Traditional models of galaxy evolution don't always work well when applied to compact groups, meaning that astronomers have to develop entirely new ways of thinking about these systems. The interactions are so dynamic and unpredictable that even the most advanced computer simulations struggle to fully capture their behavior. This is why direct observations are so important. Every new image taken of a compact galaxy group gives us another piece of the puzzle. New discoveries are constantly reshaping our understanding. In recent years, astronomers have detected strange radio signals coming from some compact groups, suggesting that they might host previously unknown cosmic phenomena. Some groups have also been found to contain incredibly massive clouds of intergalactic gas that extend far beyond what we would expect based on their galaxies alone. These observations hint at even more complex interactions taking place, possibly involving unseen forces or exotic forms of matter. Ultimately, the study of compact galaxy groups is about more than just understanding a few unusual collections of galaxies. It's about uncovering the hidden forces that shape the universe. Every time we look at a compact group, we are seeing the universe in action, watching galaxies collide, merge, and transform in ways that will determine their fates for billions of years to come. These groups challenge our assumptions, force us to rethink what we know, and push the boundaries of our understanding. And perhaps most exciting of all, they remind us that the universe is still full of surprises. No matter how much we learn, there will always be more mysteries waiting to be uncovered, hidden in the depths of space, just beyond our reach. Compact galaxy groups are among the most dynamic and perplexing environments in the cosmos. They are not just collections of galaxies, they are laboratories for some of the most extreme astrophysical processes we know. The gravitational forces at play in these tightly packed regions create interactions that would be impossible in more isolated settings. When galaxies are forced into close quarters, their fates become intertwined in ways that can reshape their structures, trigger massive bursts of star formation, and even determine whether they survive as independent galaxies or merge into something entirely new. One of the most fascinating aspects of compact galaxy groups is the presence of enormous amounts of intergalactic gas that is often stripped from the galaxies themselves. When galaxies pass too close to one another, their gravitational interactions can pull streams of gas out into the space between them, forming what are known as tidal tails. These vast, ribbon-like structures can stretch across hundreds of thousands of light-years, glowing faintly as they reflect the light of nearby stars. But here's the twist. Some of these tidal tails contain enough material to form entirely new galaxies. In other words, galaxy interactions within compact groups might not only destroy galaxies but also create new ones in the process. This raises a big question. How many of the galaxies we see today were actually born in the chaotic environments of compact groups rather than forming in isolation? If a significant fraction of galaxies were created this way, it could change our entire understanding of how structure emerges in the universe. Another strange phenomenon found in compact groups is the presence of orphan stars, stars that have been ejected from their home galaxies due to gravitational interactions. These stars now drift through intergalactic space, no longer bound to any particular galaxy. Some of them remain in small clusters, while others are entirely alone, isolated in the dark void between galaxies. There are estimates that billions of these rogue stars exist in the universe, and many of them may have originated from violent encounters between galaxies and compact groups. And then there's the mystery of dark matter. Compact galaxy groups provide some of the best evidence for the existence of dark matter, the invisible substance that makes up most of the universe's mass. When astronomers measure the motions of galaxies in these groups, they often find that the galaxies are moving much faster than they should be based on the amount of visible matter present. This suggests that there is an unseen force holding the group together, something with mass, but no light. But here's where things get weird. Some compact galaxy groups appear to contain almost no dark matter at all. This is a huge puzzle because dark matter is thought to be essential for galaxy formation. If we find galaxies that lack dark matter, it means we might have to completely rethink our models of how galaxies form and evolve. Are these galaxies exceptions, or are they hinting at an entirely new kind of physics? Even stranger, some compact groups show evidence of dark matter that extends far beyond the visible galaxies. This suggests that dark matter might not always be concentrated within galaxies, but could instead be spread out over much larger areas. This raises new questions about how dark matter interacts with normal matter, and whether our understanding of gravity itself needs to be revised. Observations of compact groups have also revealed some of the most extreme examples of starburst activity in the universe. A starburst galaxy is one that is forming stars at an exceptionally high rate, sometimes hundreds, or even thousands of times faster than a normal galaxy like the Milky Way. These bursts of star formation are often triggered by collisions and interactions within compact groups, which funnel vast amounts of gas into small regions, igniting the birth of millions of new stars in a short period of time. But these starbursts don't last forever. In many cases, they burn through their available gas in just a few million years, leaving behind galaxies that are suddenly devoid of the material needed to form new stars. This can cause galaxies to age prematurely, becoming red and dead, much earlier than they would have if they had evolved in isolation. This cycle of creation and destruction makes compact groups some of the most dynamic places in the universe, constantly reshaping themselves over cosmic timescales. And yet, despite their chaotic nature, they seem to follow certain patterns. Many compact groups appear to be in specific stages of evolution. Some are just beginning to interact, while others are in the middle of violent collisions, and still others have already merged into a single, massive galaxy. By studying compact groups at different stages, astronomers can piece together a timeline of galaxy evolution. This is why Stephan's Quintet, one of the most famous compact groups, is so important. It provides a snapshot of multiple stages of interaction happening all at once, allowing scientists to test their theories about how galaxies change over time. But there are still countless mysteries left to solve. Why do some compact groups remain stable for billions of years while others merge rapidly? What determines whether a galaxy will survive an interaction or be torn apart? Could the extreme environments of compact groups be responsible for some of the rarest and most unusual types of galaxies in the universe? One of the biggest challenges in answering these questions is that compact groups are incredibly difficult to study in detail. Their galaxies are so close together that it's often hard to tell where one ends and another begins. Dust and gas obscure many of the interactions taking place, and some of the most important processes, like the movement of dark matter, can't be directly observed at all. This is where new technology is making a difference. The James Webb Space Telescope and other next-generation observatories are giving us an unprecedented look at the hidden details of compact groups. Infrared imaging allows us to see through the dust and reveal the true structures of these galaxies. Advanced spectroscopy lets us measure the precise motions of stars and gas, giving us clues about the unseen forces at work. And perhaps most exciting of all, gravitational wave detectors are beginning to play a role in studying compact groups. When two supermassive black holes collide, a process that happens more frequently in compact groups than almost anywhere else, it creates ripples in spacetime that can be detected across the universe. By analyzing these waves, we can learn more about the final stages of galaxy mergers and the role that black holes play in shaping the evolution of compact groups. But even with all this new data, compact galaxy groups remain one of the biggest puzzles in astrophysics. Every time we think we understand them, new discoveries challenge our assumptions and force us to rethink what we know. These small, dense groups of galaxies may hold the key to some of the biggest questions in cosmology, from the nature of dark matter to the origins of the universe's most massive structures. And as we continue to explore them, one thing is certain: the universe is far more complex and mysterious than we ever imagined. The galaxies and compact groups are locked in a dance that has been going on for billions of years, and through them, we are getting a glimpse into the forces that have shaped the cosmos itself. Compact galaxy groups are not just regions of intense galactic interaction, they are cosmic battlegrounds where the laws of physics are pushed to their limits. The extreme conditions within these groups offer some of the best opportunities to test our understanding of gravity, dark matter, and galaxy evolution. When galaxies are packed so closely together, their gravitational fields become entangled in ways that would be impossible in less dense regions of space. This creates a chaotic environment where galaxies are constantly pulling on one another, stripping away gas, distorting each other's shapes, and sometimes even merging into a single entity. One of the strangest aspects of compact groups is that they seem to defy the usual rules of galaxy distribution. Most galaxies in the universe are found in larger clusters, spread out over vast distances, yet compact groups are unusually dense, with galaxies crammed together in a space that would normally hold just one or two. This raises an interesting question: how do these groups form in the first place? Did they originate in a single region of the early universe, or did they come together over time due to gravitational attraction? Astronomers believe that compact groups may be the remnants of much larger galactic structures that have evolved over billions of years. In the early universe, galaxies were more tightly packed than they are today, and as cosmic expansion stretched space itself, many galaxies moved apart. However, in regions where gravity was strong enough, some galaxies remained gravitationally bound, preventing them from drifting away. Over time, these gravitationally bound galaxies fell closer together, eventually forming the compact groups we observe today. One of the best examples of a compact group undergoing this process is Stephan's Quintet. At first glance, this group appears to contain 5 galaxies interacting in a chaotic, gravitational dance. However, upon closer examination, astronomers realize that one of these galaxies is actually much closer to us than the others. It only appears to be part of the group due to our line of sight. This discovery forced scientists to rethink how they identify compact groups and raised the possibility that many of the groups we've studied might not be as tightly bound as we once thought. But even with this new understanding, Stephan's Quintet remains a fascinating case study. The galaxies within it are tearing each other apart, their delicate structures warping as they exchange streams of gas and dust. Some of these interactions are so violent that they have triggered massive shock waves, heating the surrounding gas to millions of degrees. In fact, observations from telescopes like the Chandra X-ray Observatory have revealed that Stephan's Quintet contains some of the hottest intergalactic gas ever recorded. This raises another mystery: what happens to this gas over time? Normally, when gas is stripped from galaxies, it is either pulled into new structures or it eventually cools and settles into a new configuration. But in compact groups, some of this gas appears to remain trapped in intergalactic space, creating vast reservoirs of hot plasma that seem to persist for billions of years. These hot gas clouds emit X-rays, making them visible to high-energy telescopes, yet their exact role in galaxy evolution remains unclear. Are they a temporary byproduct of interactions, or do they serve some deeper purpose in the cosmic ecosystem? Another bizarre feature of compact groups is their tendency to harbor supermassive black holes at their centers. While most galaxies contain black holes, the extreme conditions within compact groups make these black holes far more active than usual. When galaxies interact, they funnel enormous amounts of gas toward their centers, providing the fuel needed to ignite these black holes into quasars, some of the brightest objects in the universe. These quasars unleash powerful jets of energy that can alter the course of galaxy evolution. In some cases, they drive gas out of galaxies, preventing new stars from forming. In others, they trigger bursts of star formation by compressing the surrounding gas. This dual nature of supermassive black holes means they can act as both creators and destroyers, shaping the fate of entire galaxies within compact groups. One of the most exciting recent discoveries in compact galaxy groups is the presence of ultra-diffuse galaxies. These ghostly galaxies contain very few stars but spread out over vast distances, making them almost invisible in normal optical surveys. Some of these galaxies appear to have almost no dark matter, while others seem to be made almost entirely of dark matter, with very little visible matter at all. This strange contradiction has led some scientists to propose radical new theories about the nature of dark matter and how it interacts with normal galaxies. Could it be that dark matter behaves differently in the extreme environments of compact groups? Some researchers have suggested that dark matter might be interacting with itself in ways that we don't yet understand, forming structures that remain hidden except in the most extreme gravitational environments. If this is true, compact galaxy groups could be one of the best places to study the fundamental properties of dark matter, potentially leading to breakthroughs in our understanding of the universe's invisible mass. But compact groups are not just laboratories for astrophysics. They are also time capsules, preserving ancient galactic structures that might have otherwise been destroyed. Because these groups have remained gravitationally bound for billions of years, they provide a window into the past, allowing astronomers to study galaxies that have remained relatively unchanged since the early universe. Some compact groups contain galaxies that appear to be frozen in time, their stars and structures resembling those found in the first few billion years after the Big Bang. This raises another fascinating possibility. Could compact groups be the missing link between the early universe and modern galaxy clusters? If these groups formed from the remnants of ancient galaxy structures, they might contain clues about how the first galaxies in the universe assembled and evolved. Studying them in greater detail could help astronomers piece together the missing chapters of cosmic history, filling in the gaps between the formation of the first stars and the vast galaxy clusters we see today. But the biggest mystery of all might be what happens to compact galaxy groups in the distant future. Will they continue to exist for billions of years, locked in an eternal gravitational struggle? Or will they eventually merge into single, giant galaxies, erasing all traces of their former identities? Observations suggest that many compact groups are already in the process of merging, with their galaxies slowly spiraling toward one another under the relentless pull of gravity. This means that compact groups might not be permanent structures at all, but rather a fleeting phase in the life cycle of galaxies. If this is true, then what we see today might be a brief glimpse into a process that has been happening for billions of years and will continue long after our own galaxy has changed beyond recognition. As technology advances, we will be able to study compact galaxy groups in greater detail than ever before. New telescopes, like the Vera C. Rubin Observatory, will provide deeper and more precise images of these mysterious regions, while next-generation space missions will allow us to probe their hidden depths. But for now, compact galaxy groups remain one of the greatest enigmas in astrophysics. A place where galaxies collide, dark matter reveals its secrets, and the universe itself offers us a glimpse into its most chaotic and mysterious processes. The more we study compact galaxy groups, the more we realize they are unlike anything else in the universe. They are places of violent collisions, where galaxies rip each other apart, sending streams of stars and gas careening into intergalactic space. But they are also places of creation, where gravitational interactions trigger bursts of star formation, igniting new generations of stars in the aftermath of destruction. The balance between these two forces, creation and destruction, is what makes compact galaxy groups so fascinating. One of the biggest questions astronomers are still trying to answer is how long these groups remain in their compact form before they inevitably merge into a single massive galaxy. Observations suggest that some compact groups have existed in their current state for billions of years, defying expectations that they should merge much more quickly. This raises the possibility that there might be unseen forces at play, slowing down or even preventing full mergers. One idea is that the hot gas in compact groups plays a critical role in regulating galactic interactions. When galaxies pass close to each other, they don't just exchange stars and gas, they also interact with the surrounding intergalactic medium, which can act as a kind of cosmic buffer. If this gas is hot enough, it can prevent galaxies from falling together too quickly, allowing them to remain in a semi-stable configuration for much longer than expected. But this only leads to more questions. Where does this hot gas come from? Is it a leftover relic from the early universe, or is it constantly replenished by galactic interactions? Some studies suggest that the gas is enriched with heavy elements, meaning it must have originated from within galaxies and was later expelled through processes like supernova explosions or quasar outflows. If this is true, then compact galaxy groups might serve as important reservoirs of material that will eventually be recycled into new generations of stars and galaxies. Another major mystery is the role that dark matter plays in compact galaxy groups. Most galaxies are thought to be surrounded by massive halos of dark matter, which provide the gravitational glue that holds them together. But in the extreme environments of compact groups, dark matter may behave differently than it does elsewhere in the universe. Some simulations suggest that dark matter could become more concentrated in these regions, creating gravitational wells that are much deeper than expected. This could explain why some compact groups remain bound together for so long. It's not just the visible matter keeping them together, but also an invisible web of dark matter acting behind the scenes. If this is the case, then studying compact groups could provide crucial insights into the nature of dark matter itself. By analyzing how galaxies move within these groups, astronomers can infer the distribution of dark matter and compare it to theoretical models. If discrepancies arise, it could mean that our current understanding of dark matter is incomplete, potentially pointing toward new physics beyond the standard model. One of the most puzzling discoveries in recent years is the existence of compact galaxy groups that appear to lack dark matter altogether. Normally, dark matter is expected to be the dominant mass component in any galaxy, yet some ultra-diffuse galaxies within compact groups appear to contain little or no dark matter at all. This contradicts everything we thought we knew about galaxy formation and raises the question: how did these galaxies form, and why do they behave so differently from others? One possible explanation is that these galaxies were once part of larger systems that were violently stripped of their dark matter during past interactions. If a galaxy passed too close to a more massive neighbor, gravitational forces could have pulled away much of its dark matter halo, leaving behind only the visible stars. This would mean that some compact groups contain galaxies that are essentially the remnants of past mergers, providing valuable clues about the history of galaxy interactions. Another possibility is that these galaxies formed in environments where dark matter was never abundant to begin with. If this is true, it could mean that our understanding of galaxy formation is missing a crucial piece of the puzzle. Compact groups might then hold the key to solving one of the biggest mysteries in astrophysics. What is dark matter, and how does it shape the evolution of the universe? Beyond the mysteries of dark matter and galactic evolution, compact groups also provide a unique window into the physics of star formation. When galaxies interact, they can trigger massive bursts of star formation, producing clusters of young, hot stars in a process known as starburst activity. In some cases, entire galaxies can be transformed by these interactions, turning from quiet, passive systems into intense star-forming factories. These starbursts are not just interesting from a galactic perspective, they also have profound implications for the chemical evolution of the universe. The massive stars formed in these bursts live short, explosive lives, ending in supernovae that enrich the surrounding gas with heavy elements like carbon, oxygen, and iron. Over time, this enriched material will be incorporated into new generations of stars, planets, and even life itself. This raises an intriguing question. Could compact galaxy groups be among the most important environments for seeding the universe with the building blocks of life? If so, then the chaotic interactions within these groups might not just be cosmic accidents, but rather essential processes that help shape the conditions necessary for planets and life to emerge elsewhere in the cosmos. As astronomers continue to study compact galaxy groups, they are beginning to realize that these regions are far more complex than they first appeared. They are not just clusters of galaxies, they are dynamic, evolving ecosystems, where the interplay of gravity, gas dynamics, and dark matter creates some of the most extreme conditions in the universe. With the next generation of telescopes, such as the James Webb Space Telescope and the upcoming Extremely Large Telescope, scientists will be able to probe compact groups in unprecedented detail. These new observations could reveal even more surprises, potentially rewriting our understanding of how galaxies interact and evolve. But even with all of these advances, one thing is certain: compact galaxy groups will continue to be one of the most mysterious and fascinating phenomena in the universe. They challenge our theories, push the limits of our knowledge, and remind us that the cosmos is far more complex and unpredictable than we could ever imagine. Compact galaxy groups are more than just clusters of galaxies. They are cosmic laboratories where the fundamental processes of galactic evolution unfold in real time. These environments offer unique insights into the life cycles of galaxies, the nature of dark matter, and the intricate dance of gravitational interactions. But despite decades of research, they continue to defy expectations and raise new questions about the fundamental forces shaping the universe. One of the most perplexing aspects of compact groups is their diversity. Some groups appear relatively stable, with galaxies slowly orbiting each other over billions of years. Others are in the midst of dramatic mergers, with streams of stars and gas stretching across vast distances as galaxies collide and merge into larger structures. This raises an important question: what determines the fate of a compact galaxy group? One theory suggests that the initial conditions of a group, such as the masses of the galaxies, their relative velocities, and the amount of dark matter present, play a crucial role in determining how the group evolves. If the galaxies have low relative velocities, they are more likely to merge quickly, forming a single massive galaxy within a few billion years. But if their velocities are higher, they may remain in a delicate balance, with gravitational interactions constantly reshaping the group without leading to an immediate merger. Another factor that may influence the evolution of compact groups is the presence of intergalactic gas. Many compact groups are filled with hot, ionized gas that can slow down or even prevent galaxy mergers by exerting pressure on the galaxies. This gas can also act as a medium for shock waves and turbulence, triggering bursts of star formation in some galaxies while stripping others of their gas and halting star formation entirely. The interplay between gas dynamics and gravitational forces is a complex and poorly understood process, but it is clear that it plays a major role in shaping the destiny of compact galaxy groups. But perhaps the most intriguing question is what happens to compact groups over cosmic time. Do they always merge into a single galaxy, or can they remain in a stable configuration indefinitely? Some studies suggest that certain compact groups may never fully merge, instead evolving into loose associations of galaxies that continue interacting for billions of years. These fossil groups are thought to be the remnants of compact groups that have lost most of their smaller galaxies, leaving behind a single massive galaxy surrounded by a halo of hot gas and dark matter. If fossil groups are indeed the end state of many compact groups, this could have profound implications for our understanding of galaxy evolution. It would suggest that many of the massive elliptical galaxies we see today may have originated from compact groups that underwent a series of mergers over time. This idea is supported by observations of large elliptical galaxies with extended halos of stars and gas, which may be the remnants of past interactions in a now dispersed compact group. However, not all compact groups follow this path. Some appear to be in a state of near-perpetual interaction, with galaxies repeatedly passing close to each other without fully merging. This raises the possibility that there may be unseen factors at play, perhaps exotic forms of dark matter, or even previously unknown gravitational effects, that allow some groups to resist merging for much longer than expected. Another mystery surrounding compact galaxy groups is their connection to large-scale cosmic structures. The universe is not randomly distributed. Rather, galaxies are arranged in vast cosmic webs, with dense clusters of galaxies connected by filaments of gas and dark matter. Compact groups are often found in the outskirts of these larger structures, raising the question of whether they are remnants of larger clusters that have fragmented over time, or whether they represent an early stage in the formation of new galaxy clusters. Some astronomers believe that compact groups may serve as bridges between different regions of the cosmic web, acting as nodes where galaxies and gas streams converge. If this is true, then studying these groups could provide crucial insights into how matter is distributed on the largest scales in the universe. The role of dark matter in compact groups remains one of the biggest unsolved mysteries in astrophysics. While most galaxies are thought to be embedded in massive halos of dark matter, some observations suggest that compact groups may have an unusually high concentration of dark matter, while others appear to lack it entirely. This contradiction has led to intense debate among scientists, with some arguing that compact groups provide evidence for new physics beyond the standard model of cosmology. One possibility is that dark matter behaves differently in compact groups than it does in other environments. If dark matter particles can interact with each other through forces beyond gravity, then this could explain why some groups appear to have more dark matter than expected, while others seem to have lost it entirely. If confirmed, this would represent a major breakthrough in our understanding of dark matter and could provide clues about its fundamental nature. Compact groups also provide a unique testing ground for theories of galaxy formation and evolution. In traditional models, galaxies are thought to grow through a combination of mergers and gas accretion, gradually building up their mass over billions of years. But compact groups challenge this view by showing that galaxies can undergo rapid transformations in highly dynamic environments. Some galaxies in compact groups appear to be stripped of their gas and stars at an accelerated rate, suggesting that interactions in these environments may play a much larger role in galaxy evolution than previously thought. Observations of compact groups have also revealed a surprising number of orphan stars, individual stars that have been ejected from their parent galaxies during interactions. These stars drift through intergalactic space, forming faint halos around compact groups. The presence of these orphan stars provides a valuable way to trace past interactions, allowing astronomers to reconstruct the history of a group and determine how its galaxies have evolved over time. One of the most exciting developments in recent years is the discovery of compact groups in the early universe. Thanks to powerful telescopes like the James Webb Space Telescope, astronomers are now able to observe these groups as they appeared billions of years ago, providing a glimpse into the processes that shaped the first galaxies. These early compact groups appear to be even more dynamic than their modern counterparts, with galaxies merging at an accelerated rate and undergoing rapid bursts of star formation. This raises an intriguing question: could compact groups have played a key role in shaping the structure of the universe as we see it today? If these groups were common in the early universe, then they may have served as the building blocks for larger galaxy clusters, influencing the distribution of matter on the largest scales. If so, then studying these groups could help us unravel some of the deepest mysteries of cosmology, including how galaxies first formed and why the universe looks the way it does today. As we continue to explore compact galaxy groups, one thing is certain: they are far more than just collections of galaxies. They are dynamic, evolving systems that challenge our understanding of gravity, dark matter, and the nature of the cosmos itself. Every new discovery brings fresh questions, reminding us that the universe is full of surprises waiting to be uncovered. With future telescopes and simulations, we are on the brink of unlocking even more secrets about these mysterious groups. Whether they hold the key to understanding dark matter, the formation of the first galaxies, or the ultimate fate of galactic systems, one thing is clear: the study of compact galaxy groups is only just beginning. As we continue to explore the mysteries surrounding compact galaxy groups, it becomes increasingly clear that these environments are far more than just observational curiosities. They represent dynamic laboratories where astronomers can test the limits of our understanding of the universe's fundamental forces. The interactions within these groups reveal complex and fascinating processes that might be at the heart of some of the universe's most significant and puzzling phenomena. One of the most remarkable aspects of compact galaxy groups is how they challenge the traditional view of galaxy formation. In the conventional model, galaxies are thought to form primarily through the gradual accumulation of gas and stars over time, along with mergers and accretion events that lead to massive, stable structures. However, the conditions in compact groups appear to accelerate or even reverse this process. Galaxies in these environments can undergo rapid transformations due to the extreme gravitational interactions that occur when multiple galaxies are in close proximity. The high density of galaxies within compact groups often leads to frequent and intense interactions, including tidal stripping, galaxy mergers, and starbursts. Tidal stripping occurs when one galaxy passes too close to another, causing its outer regions, primarily gas and stars, to be pulled away by the gravitational forces of the neighboring galaxy. This phenomenon can lead to the disruption of galaxies, triggering bursts of star formation or, in some cases, stripping them of the material necessary to form new stars, leaving behind an older, redder galaxy. Interestingly, some compact galaxy groups seem to defy the predictions of the standard models of galaxy formation. In these groups, the galaxies do not always follow the expected patterns of star formation. Instead of forming new stars in an orderly manner, they can experience chaotic bursts of star formation as a result of their close interactions. The gravitational forces at play in these dense environments can compress gas clouds, triggering rapid star birth and potentially fueling the formation of supermassive black holes at the centers of the galaxies. In extreme cases, these processes can result in the complete transformation of a galaxy, turning it into a passive, gas-depleted system with little new star formation. The role of dark matter in these interactions is another area of active research. Dark matter, the mysterious substance that is thought to make up the majority of the universe's mass, is believed to exert a powerful gravitational influence on galaxies. In compact groups, the distribution of dark matter is often not as simple as it appears. Some studies suggest that dark matter halos in compact groups may be significantly more concentrated than in isolated galaxies. This could imply that the gravitational interactions within compact groups are shaped not only by the visible matter, such as stars and gas, but also by the invisible, yet dominant, presence of dark matter. The varying amounts of dark matter in different compact galaxy groups could also help explain why some groups evolve in one way while others take a different path. For instance, groups with larger dark matter concentrations may be able to maintain their structure over longer periods, preventing galaxies from merging too quickly. This could help explain the existence of some compact groups that remain in a state of prolonged interaction without fully merging into a single galaxy. On the other hand, groups with less dark matter may be more prone to rapid mergers, resulting in the creation of more massive galaxies over shorter timescales. In addition to their role in the evolution of galaxies, compact groups also provide valuable insight into the behavior of intergalactic gas. Many compact groups are filled with hot, diffuse gas that fills the space between galaxies. This gas can serve as a medium for various astrophysical processes, including the propagation of shockwaves and the transfer of energy between galaxies. The gas in these environments is often highly ionized, and it can provide important clues about the thermal and chemical history of the universe. Recent observations have shown that compact groups may host some of the most extreme examples of intergalactic gas. In some cases, the gas is so hot that it reaches temperatures of millions of degrees, making it difficult for galaxies to retain their gas and continue forming stars. This phenomenon is known as ram pressure stripping, and it occurs when a galaxy moves through a dense gas environment at high speeds, stripping away its outer layers of gas. This process can suppress star formation, leaving galaxies gas-depleted and unable to form new stars for billions of years. But it's not all doom and gloom for galaxies in compact groups. While ram pressure stripping can prevent some galaxies from forming new stars, it can also trigger bursts of star formation in other galaxies. As gas is stripped from one galaxy, it can be compressed into neighboring galaxies, potentially triggering a new wave of star birth. This process can lead to the creation of young, star-forming regions in what were once passive galaxies, and it may play a significant role in the evolution of compact groups over time. What makes these processes particularly fascinating is their ability to shape the future of the universe itself. The interactions that occur in compact galaxy groups are not just important for understanding the life cycles of individual galaxies. They also have profound implications for the larger-scale structure of the cosmos. As these groups evolve, they may provide important clues about the formation and fate of galaxy clusters, the largest structures in the universe. Some theories suggest that compact groups may serve as seeds for the formation of larger galaxy clusters. In this scenario, compact groups would represent the early stages of galaxy cluster formation, where galaxies are still undergoing intense interactions and mergers. Over time, these groups would coalesce into more massive clusters, which could then go on to merge with other clusters, ultimately forming the superclusters that make up the cosmic web. Another important question is how compact galaxy groups fit into the broader picture of dark energy and the expansion of the universe. As we've learned, the expansion of the universe is accelerating, driven by the mysterious force known as dark energy. But how does this force interact with the dense environments found in compact galaxy groups? Could dark energy play a role in the interactions between galaxies in these groups, perhaps by influencing their motion or altering the way in which they merge? The answer to this question remains elusive, but it is a key area of research that could help us understand the ultimate fate of the universe itself. Looking ahead, the study of compact galaxy groups is poised to make even greater strides thanks to the next generation of space telescopes. Instruments like the James Webb Space Telescope and the upcoming Square Kilometre Array will allow astronomers to observe these groups in unprecedented detail, uncovering new insights into the processes that govern their evolution. These observations may provide the missing pieces of the puzzle when it comes to understanding dark matter, galaxy formation, and the large-scale structure of the universe. In addition to new telescopes, advancements in computational simulations are also expected to play a critical role in our understanding of compact galaxy groups. By simulating the interactions between galaxies, gas, and dark matter within these groups, scientists can gain a better understanding of how these environments evolve over time and how they might have influenced the formation of galaxies and clusters in the early universe. As we uncover more about these enigmatic cosmic environments, we are left with a profound sense of wonder at the complexity and beauty of the universe. Compact galaxy groups, with their intricate webs of gravitational interactions, dark matter, and gas dynamics, represent some of the most exciting and mysterious phenomena in modern astronomy. They challenge our understanding of galaxy evolution, dark matter, and the forces that shape the universe. And with each new discovery, we come one step closer to unlocking the secrets of these fascinating cosmic systems. Compact galaxy groups continue to hold a special place in our quest for understanding the universe. Their unique configurations of galaxies, dark matter, and gas make them fascinating objects of study for astronomers, and they often serve as natural laboratories for testing astrophysical theories. These groups provide insights not only into the interactions between galaxies but also into broader cosmological phenomena that influence the evolution of the universe as a whole. One key area of interest is the role of compact galaxy groups in the context of the larger cosmic structure. When we look at the universe on a grand scale, we see that galaxies are not evenly distributed. Instead, they are found in clusters, groups, and vast empty regions known as voids. Compact galaxy groups are intermediate structures in this cosmic hierarchy, bridging the gap between isolated galaxies and massive galaxy clusters. These groups are often in the process of merging or interacting, and they may eventually evolve into larger clusters, offering astronomers a glimpse into the future of galaxy evolution. In fact, the study of compact galaxy groups is crucial for understanding how galaxy clusters themselves form and evolve. While galaxy clusters are the most massive structures in the universe, their formation is still not entirely understood. However, by examining the interactions and dynamics within compact galaxy groups, scientists can begin to piece together the story of how galaxies come together to form these immense structures. The evolution of galaxy clusters is a complex process that involves the merging of smaller groups, the accretion of intergalactic gas, and the influence of dark matter. As compact galaxy groups continue to merge and interact, they can provide valuable information about the mechanisms that govern the growth of galaxy clusters and the larger-scale structure of the universe. Moreover, the dense environments within compact groups can offer critical insights into the behavior of the most extreme objects in the universe, such as supermassive black holes. These black holes, found at the centers of most galaxies, play a pivotal role in shaping their evolution. In some cases, the gravitational interactions between galaxies and compact groups can trigger the growth of supermassive black holes, leading to the formation of active galactic nuclei, AGNs. These AGNs are incredibly bright and energetic, emitting large amounts of radiation as matter falls into the black hole. Studying the formation and behavior of AGNs in compact galaxy groups can help us understand the role of black holes in galaxy formation and evolution, as well as their connection to the larger cosmic environment. The study of compact galaxy groups also has implications for our understanding of the dark matter that permeates the universe. Dark matter, an invisible substance that accounts for a significant portion of the universe's mass, plays a crucial role in the formation of galaxies and clusters. In compact galaxy groups, dark matter can influence the dynamics of galaxy interactions, the distribution of gas, and the overall gravitational structure of the group. By studying how dark matter behaves in these dense environments, astronomers can refine their models of dark matter and better understand its role in shaping the universe. As our understanding of compact galaxy groups continues to evolve, it is becoming clear that these groups are not just the curiosity of the cosmos but are essential to understanding the larger processes that govern the universe's evolution. The interactions between galaxies, gas, and dark matter in these groups offer valuable clues about the nature of the universe itself, from the formation of galaxies and clusters to the behavior of dark matter and the growth of supermassive black holes. Looking ahead, the study of compact galaxy groups is likely to continue to be a major focus of astronomical research. With the advent of more advanced telescopes and observatories, such as the James Webb Space Telescope, scientists will be able to study these groups in unprecedented detail. Observing the dynamics of these groups in various wavelengths of light, from radio waves to X-rays, will allow researchers to gain deeper insights into the processes that shape the evolution of galaxies and their interactions. In addition to advanced telescopes, the development of new computational models and simulations will play a key role in advancing our understanding of compact galaxy groups. These models allow scientists to simulate the gravitational interactions between galaxies, gas, and dark matter in a way that would be impossible through direct observation alone. By running simulations of compact galaxy groups, astronomers can test different theories about galaxy formation, dark matter, and the evolution of cosmic structures. These simulations are crucial for making predictions about how these systems will evolve over time and for understanding the long-term effects of galaxy interactions in dense environments. Moreover, the study of compact galaxy groups may also have broader implications for understanding the early universe. Some compact groups are thought to represent systems that formed early in the history of the cosmos, potentially offering a glimpse into the processes that took place shortly after the Big Bang. By studying these groups, astronomers can learn more about the conditions that led to the formation of the first galaxies and the evolution of cosmic structures over billions of years. These insights may ultimately help us answer some of the most fundamental questions about the origin and evolution of the universe itself. Compact galaxy groups are among the most intriguing and valuable objects of study in modern astrophysics. Their dense, dynamic environments offer a wealth of information about the processes that govern galaxy formation, dark matter, and the large-scale structure of the universe. As we continue to explore these fascinating cosmic systems, we gain new insights into the nature of the universe and the forces that shape it. With advanced telescopes, simulations, and observational techniques, we are poised to uncover even more about these enigmatic groups and the mysteries they hold. Each new discovery brings us one step closer to understanding the complex and beautiful universe in which we live. As we dive deeper into the study of compact galaxy groups, we can begin to explore some of the specific phenomena that occur within these environments. One of the most striking aspects of compact galaxy groups is the way that galaxies within these groups interact with each other, often undergoing violent and dramatic changes as a result of gravitational forces. The galaxies within these groups are often on highly elliptical orbits, meaning that they come close to each other at certain points in their orbits, only to be flung away at other times. These interactions, while chaotic, play a crucial role in the evolution of the galaxies themselves, leading to changes in their structure, morphology, and star formation rates. One of the key outcomes of these interactions is the process known as galaxy merging. As galaxies collide and pass through each other, their gravitational forces can distort their shapes, leading to the formation of new, more massive galaxies. In some cases, these mergers result in the formation of elliptical galaxies, which are characterized by their smooth, featureless shapes and the lack of significant ongoing star formation. The merger process can trigger bursts of star formation, as gas clouds within the galaxies are compressed and heated, leading to the formation of new stars. However, over time, these star-forming regions may be consumed, leaving behind a remnant galaxy that is primarily composed of older stars. This process of galaxy merging is not limited to compact galaxy groups. In fact, it is thought to be one of the primary drivers of galaxy evolution across the universe. The difference, however, is that in compact galaxy groups, these mergers can occur more frequently and more rapidly due to the dense environment. The close proximity of galaxies in these groups increases the likelihood of interactions, meaning that these systems may evolve at a faster pace than more isolated galaxies. This makes compact galaxy groups an excellent natural laboratory for studying the merger process and its effects on galaxy evolution. Another intriguing aspect of compact galaxy groups is the role of intragroup gas, or the hot, diffuse gas that exists between the galaxies within the group. This gas, which is often at temperatures of several million degrees, plays a significant role in the dynamics of the group. It can be heated through processes such as galaxy collisions, shocks from supernova explosions, and the activity of supermassive black holes. This intragroup gas is often observed in X-ray wavelengths, as the high temperatures cause it to emit radiation in this part of the electromagnetic spectrum. In addition to its role in heating the group, intragroup gas also contributes to the overall mass and energy budget of the group. In some compact galaxy groups, this gas can account for a significant fraction of the group's total mass, and its distribution can be highly influenced by the gravitational forces of the galaxies. The study of intragroup gas can provide valuable insights into the processes that govern the behavior of gas in dense environments, and how it interacts with galaxies and dark matter. It can also help scientists understand the role of feedback mechanisms, such as the activity of supermassive black holes, in regulating the growth and evolution of galaxies. Supermassive black holes, as mentioned earlier, are often found at the centers of galaxies, and their influence extends well beyond their immediate surroundings. In compact galaxy groups, the interactions between galaxies can trigger the growth of these black holes, leading to the formation of active galactic nuclei, AGNs. AGNs are among the brightest and most energetic objects in the universe, emitting vast amounts of radiation across the electromagnetic spectrum, from radio waves to X-rays. The growth of supermassive black holes in compact galaxy groups is thought to be driven by the accretion of gas from the surrounding environment. As galaxies interact, their gas can be funneled toward the centers of the galaxies, where it may eventually fall into the black hole, releasing tremendous amounts of energy in the process. This feedback, in turn, can affect the evolution of the entire group, as the energy released by the AGN can heat the surrounding gas, preventing further star formation and regulating the growth of the galaxies. Interestingly, the presence of AGNs in compact galaxy groups is not always a straightforward process. In some cases, the interactions between galaxies may lead to the suppression of AGN activity. For example, if a galaxy experiences a particularly violent collision with another galaxy, the resulting shock waves and gas flows may prevent the supermassive black hole from accreting material, effectively shutting down the AGN. This interplay between galaxy mergers, AGN activity, and the surrounding gas is still an area of active research and holds the potential to uncover new insights into the evolution of galaxies and their central black holes. As we continue to explore the dynamics of compact galaxy groups, we also begin to recognize the broader implications for our understanding of cosmology and the large-scale structure of the universe. One of the most significant questions in modern astrophysics is the nature of dark matter, the mysterious substance that accounts for a large fraction of the universe's mass. Dark matter interacts with normal matter through gravity, but it does not emit, absorb, or reflect light, making it invisible to direct observation. Its existence is inferred from its gravitational effects on galaxies, galaxy clusters, and the large-scale structure of the universe. Compact galaxy groups provide an opportunity to study dark matter in action. The gravitational forces within these groups are strong, and dark matter is thought to play a crucial role in shaping the dynamics of the group. In fact, dark matter is believed to make up the majority of the mass in these groups, with only a small fraction being composed of visible galaxies and gas. By studying the distribution of galaxies, gas, and dark matter in compact galaxy groups, scientists can gain valuable insights into the properties of dark matter, such as its density, distribution, and its role in the formation of cosmic structures. One of the challenges in studying dark matter in compact galaxy groups is that it is, by definition, invisible. However, astronomers can detect its presence through its gravitational effects on the visible matter in the group. By mapping the motions of galaxies and gas within the group, scientists can infer the distribution of dark matter and estimate its total mass. These observations, combined with sophisticated simulations, allow astronomers to test different models of dark matter and refine their understanding of this enigmatic substance. In the future, as our observational capabilities continue to improve, we may be able to make even more precise measurements of dark matter in compact galaxy groups. The next generation of telescopes, such as the James Webb Space Telescope and the upcoming ground-based observatories, will provide us with unprecedented views of these groups, allowing us to study them in greater detail than ever before. With these new tools, we may be able to unlock some of the deepest mysteries of the universe, including the nature of dark matter and its role in the formation and evolution of galaxies and large-scale cosmic structures. As we continue to explore the intricate dynamics of compact galaxy groups, we can begin to appreciate how these small, dense collections of galaxies serve as laboratories for studying large-scale cosmic phenomena. One of the most fascinating aspects of compact galaxy groups is the way in which they shed light on the process of galaxy transformation. Over time, these groups can experience a variety of evolutionary changes, with galaxies undergoing significant alterations to their structure and behavior. Understanding how compact galaxy groups evolve can help us understand the broader process of galaxy formation across the universe. In particular, compact galaxy groups are thought to be in a phase of transformation that is characterized by intense interactions between the galaxies within the group. These interactions can lead to a range of outcomes, including the complete disruption of the galaxy's original structures. For example, galaxies may experience tidal stripping, a process in which their outer layers of stars and gas are pulled away by the gravitational forces of neighboring galaxies. This process can lead to the formation of long, faint tails of stars and gas, often referred to as tidal tails. These tidal features are the signature of the gravitational interactions occurring between galaxies, and their study provides insight into the strength and nature of these forces. In some cases, the tidal interactions between galaxies within a compact galaxy group can lead to the complete stripping of a galaxy's gas. This process, known as ram pressure stripping, occurs when the gas within a galaxy is forced out of the galaxy by the pressure exerted by the hot intergroup medium. This can have profound implications for the future evolution of the galaxy. Without its gas, a galaxy is unable to form new stars, and it may eventually evolve into a red and dead galaxy, characterized by an old population of stars and little to no ongoing star formation. The study of ram pressure stripping in compact galaxy groups is crucial for understanding the fate of galaxies in dense environments, and it can help us answer important questions about the mechanisms that drive galaxy evolution. Another aspect of galaxy evolution in compact galaxy groups is the role of the intergroup medium. This hot, diffuse gas that fills the space between galaxies is not only a key factor in regulating galaxy interactions, but it also plays an important role in the energy balance of the group as a whole. The intergroup medium can act as a conduit for energy transfer between galaxies, absorbing energy from their interactions and redistributing it across the group. This process can have a profound effect on the overall structure of the group, influencing the rate of star formation in individual galaxies and the overall dynamics of the system. The intergroup gas in compact galaxy groups is often observed in the X-ray part of the electromagnetic spectrum, as the temperatures of this gas can reach millions of degrees. These X-ray observations provide a window into the properties of the intergroup medium and offer clues about its role in the evolution of the group. For example, the temperature and density of the intergroup gas can reveal information about the history of galaxy interactions in the group. In particular, regions of the gas that are heated to higher temperatures can indicate areas where galaxies have recently passed through each other, releasing energy into the surrounding gas. This allows astronomers to trace the recent history of interactions in compact galaxy groups and to understand the role of the intergroup medium in shaping the group's overall structure. The study of compact galaxy groups also offers insights into the broader cosmic web that connects galaxies, galaxy groups, and galaxy clusters. The universe is not a homogeneous, evenly distributed collection of galaxies. Instead, galaxies are organized into vast, intricate structures known as the cosmic web. These structures consist of long, thin filaments of galaxies, separated by vast voids of empty space. Compact galaxy groups are often located at the intersections of these cosmic filaments, where the gravitational forces of nearby structures can cause galaxies to gather together and form dense groups. By studying the formation and evolution of compact galaxy groups, scientists can gain a better understanding of the processes that govern the assembly of larger cosmic structures, such as galaxy clusters. These galaxy clusters, which contain hundreds or even thousands of galaxies, are the largest gravitationally bound structures in the universe. Understanding how compact galaxy groups fit into this larger cosmic puzzle is essential for understanding the large-scale structure of the universe and the processes that lead to the formation of these enormous galaxy clusters. One of the key questions in this area of research is whether compact galaxy groups can evolve into galaxy clusters over time. As compact galaxy groups undergo further interactions and mergers, it is possible that they could eventually grow into larger systems. However, this process is not straightforward, and it depends on a variety of factors, such as the relative velocities of the galaxies within the group, the amount of dark matter present in the group, and the interactions with neighboring groups and clusters. The transformation of compact galaxy groups into larger systems is an area of ongoing research, and astronomers are working to develop models that can predict how these small groups evolve over cosmic timescales. In addition to their role in galaxy evolution, compact galaxy groups are also important for understanding the broader physics of the universe. The interactions that take place in these groups are governed by the same fundamental forces that shape the rest of the universe. Studying these interactions can provide insights into the nature of dark matter, dark energy, and the fundamental laws of physics. For example, the gravitational interactions between galaxies in a compact galaxy group can be used to test models of dark matter, as the distribution of dark matter in the group influences the motion of galaxies within the group. Similarly, the study of intragroup gas can provide clues about the role of dark energy in the evolution of cosmic structures. One of the challenges in studying compact galaxy groups is the difficulty in observing them directly. These groups are often located at great distances from Earth, making it challenging to obtain detailed observations. However, recent advances in telescope technology have made it possible to observe these groups in greater detail than ever before. Instruments like the Hubble Space Telescope, the Chandra X-ray Observatory, and the upcoming James Webb Space Telescope will provide astronomers with unprecedented views of compact galaxy groups, allowing them to study their structure, dynamics, and evolution in greater detail. With these new tools, scientists hope to answer many of the outstanding questions about compact galaxy groups and their role in the larger cosmic landscape. As our understanding of compact galaxy groups continues to evolve, it is clear that these small, dense collections of galaxies are not just interesting for their own sake, but also for the broader insights they provide into the workings of the universe. The interactions between galaxies in these groups, the role of dark matter, the behavior of intragroup gas, and the processes of galaxy evolution all contribute to our understanding of the cosmos. By studying compact galaxy groups, we are not just learning about the galaxies themselves, but also about the fundamental forces and processes that govern the universe at the largest scales. Ultimately, the study of compact galaxy groups is not just an exercise in understanding the small-scale dynamics of galaxy interactions. It is also a key piece of the puzzle in our quest to understand the universe itself. As we continue to explore the mysteries of these fascinating systems, we may uncover new insights into the fundamental nature of the cosmos, the forces that shape galaxies, and the larger structures that govern the universe as a whole. Continuing the exploration of compact galaxy groups, another intriguing aspect is how these systems provide insight into the larger-scale cosmic processes that affect the evolution of galaxies and galaxy clusters. The role of these small, dense groups in galactic evolution is not only crucial for understanding the dynamics within them but also for shaping the broader structures of the universe. As we've seen, compact galaxy groups like Stephan's Quintet provide an invaluable laboratory for studying galaxy interactions and mergers. These interactions are often violent, with galaxies colliding, merging, and exchanging mass through gravitational forces. This process not only alters the structure of individual galaxies but also contributes to the reshaping of the entire group. Such interactions are thought to play a significant role in the transformation of galaxies from one type to another, specifically, from blue, star-forming galaxies to red, passive ones. The intense environment of compact galaxy groups can trigger bursts of star formation in some galaxies while simultaneously halting it in others. Understanding these interactions allows astronomers to unravel the evolutionary paths that galaxies might follow when subjected to extreme conditions. Another critical aspect of compact galaxy groups is their connection to the broader phenomenon of galaxy morphology. The types of galaxies within a compact group can be influenced heavily by their environment. For instance, some compact groups are dominated by elliptical galaxies, which are typically older, with little ongoing star formation. These elliptical galaxies are thought to form through the merger of two or more smaller galaxies, a process that often occurs within dense groups. Other compact groups, however, may contain spiral galaxies, which are younger and still actively forming stars. These galaxies can be significantly altered by their interactions with other galaxies in the group, with the spiral arms becoming distorted or the disk being flattened as a result of gravitational interactions. Interestingly, compact galaxy groups also shed light on the processes that can lead to the suppression of star formation in galaxies. In some groups, the intergroup medium, composed of hot, diffuse gas, can play a key role in this suppression. This gas can strip galaxies of their gas reservoirs, preventing the formation of new stars. Over time, this depletion of gas leads to a gradual aging of the galaxy, resulting in what is often referred to as a red and dead galaxy, one that no longer forms stars but instead consists of older, cooler stars. These types of galaxies are commonly found in the cores of galaxy clusters, where the density of galaxies is much higher. However, the transformation from a star-forming galaxy to a quiescent, gas-depleted galaxy can also occur within compact galaxy groups, especially when these groups undergo significant tidal interactions. While the study of compact galaxy groups has provided many insights into the processes of galaxy evolution, it has also raised important questions about the role of dark matter in these systems. Dark matter, the mysterious substance that accounts for the majority of the universe's mass, is thought to play a key role in shaping the dynamics of galaxies and galaxy groups. In compact galaxy groups, the distribution of dark matter can significantly influence the motion of galaxies and the behavior of the intergroup gas. For instance, the gravitational pull of dark matter may help bind galaxies together within a group, preventing them from flying apart due to the effects of their mutual interactions. Additionally, dark matter may play a role in the heating of the intergroup medium, as the gravitational interactions between galaxies can lead to the release of energy, which in turn heats the surrounding gas. Understanding the distribution and behavior of dark matter in compact galaxy groups is a key area of research that can shed light on its role in the evolution of galaxies and galaxy clusters. The study of compact galaxy groups also provides a window into the early history of the universe. Many of these groups are located at great distances from Earth, meaning we are observing them as they appeared billions of years ago. By studying these distant systems, we can gain a better understanding of how galaxies formed and evolved in the early universe. In particular, compact galaxy groups offer a glimpse into the kinds of environments in which galaxies may have first gathered together. These systems can serve as analogs for the kinds of galaxy groups that existed in the early stages of the universe, offering clues about the processes that led to the formation of larger cosmic structures, such as galaxy clusters. As we look to the future of compact galaxy group research, the development of new observational technologies promises to greatly enhance our understanding of these systems. The advent of next-generation telescopes, such as the James Webb Space Telescope, will allow astronomers to observe compact galaxy groups in unprecedented detail, enabling them to probe the physical properties of these systems with greater precision. The ability to observe compact galaxy groups in multiple wavelengths, such as optical, infrared, and X-ray, will provide a more comprehensive view of these systems, allowing scientists to study their structure, dynamics, and evolution across a wide range of energies. In addition to advancing our understanding of compact galaxy groups, These observations will also contribute to our broader understanding of galaxy formation and evolution. By studying the interactions between galaxies within compact groups, astronomers can better understand how galaxies grow and evolve over time. They can also learn more about the factors that drive the cessation of star formation in galaxies, as well as the mechanisms that regulate galaxy growth and transformation. These insights are crucial for building a complete picture of the processes that govern the universe's evolution and will contribute to answering some of the most profound questions in cosmology. One of the key challenges in studying compact galaxy groups is understanding how the interactions within these systems differ from those in larger galaxy clusters. Galaxy clusters, with their vast numbers of galaxies, offer a much more complex environment than compact groups. However, by studying compact galaxy groups, astronomers can isolate the effects of galaxy interactions in a more controlled setting, making it easier to understand the underlying processes at work. In particular, compact galaxy groups offer an opportunity to study how galaxies evolve in a relatively isolated environment, without the overwhelming influence of the large-scale gravitational forces that dominate galaxy clusters. This makes them an essential piece of the puzzle for understanding galaxy formation and evolution in the universe. Another critical factor in the study of compact galaxy groups is their connection to larger-scale structures in the universe. As we've mentioned, compact galaxy groups are often located at the intersections of cosmic filaments, which are part of the vast cosmic web that forms the large-scale structure of the universe. These filaments are made up of galaxies, galaxy groups, and dark matter, all of which are connected by gravitational forces. The study of compact galaxy groups can therefore provide valuable insights into the processes that govern the formation of these cosmic structures. By understanding how compact galaxy groups fit into the larger cosmic web, astronomers can learn more about the evolution of the universe on the largest scales. The study of compact galaxy groups provides a unique and valuable opportunity to understand the processes that drive the evolution of galaxies and the large-scale structure of the universe. These small, dense collections of galaxies are not just interesting for their own sake, but also for the broader insights they offer into the workings of the cosmos. Through the study of compact galaxy groups, we can learn about the forces that shape galaxies, the role of dark matter in galaxy evolution, and the mechanisms that govern the formation of larger cosmic structures. As our understanding of these systems continues to evolve, it is likely that we will uncover new and exciting discoveries that will reshape our view of the universe and the forces that govern its evolution. Continuing the exploration of compact galaxy groups, it's important to note that these systems are not just fascinating for what they can tell us about the present state of the universe, but they also provide a critical window into the distant past. The study of compact galaxy groups, especially those observed at high redshifts, allows astronomers to look back billions of years to when these groups first began to form. This gives us a unique opportunity to study galaxy formation and evolution in a much earlier, less mature universe. High redshift compact galaxy groups are particularly interesting because they are often seen at a time when galaxy interactions were more common. During the early stages of the universe, galaxies were much closer together, and the frequency of galactic mergers and interactions was higher than it is today. In fact, many of the compact galaxy groups that we observe at great distances are thought to be relics of this earlier, more chaotic era in cosmic history. By studying these distant systems, astronomers can gain valuable insights into how galaxy groups form, how galaxies grow and evolve, and how the large-scale structure of the universe developed over time. These high redshift observations also provide clues about the role of feedback processes in the evolution of galaxies. In particular, the interaction between galaxies and the hot, diffuse gas that permeates these groups can have a profound effect on the galaxies within them. This intergroup medium, which is often composed of hot gas heated to millions of degrees, can strip galaxies of their gas, preventing them from forming new stars and contributing to the quenching of star formation. The study of how this process occurs in compact galaxy groups can provide valuable insights into the feedback mechanisms that regulate galaxy growth and star formation. Furthermore, compact galaxy groups offer an important avenue for studying the impact of galaxy mergers on the evolution of galaxies. In many cases, compact groups are formed as a result of galaxy mergers, where the gravitational forces between galaxies cause them to collide and merge into a single, larger galaxy. These mergers can have a profound effect on the galaxies involved, triggering bursts of star formation, distorting galaxy shapes, and often leading to the formation of elliptical galaxies. By studying the remnants of these mergers in compact galaxy groups, astronomers can better understand the role of galaxy collisions in the formation of galaxy clusters and the evolution of the cosmic web. Another important aspect of compact galaxy groups is their role in the broader study of the cosmic web. The cosmic web, the large-scale structure of the universe, consists of vast filaments of galaxies and dark matter, interconnected by vast voids. Compact galaxy groups are often located at the intersections of these cosmic filaments, serving as a crucial link in the larger structure of the universe. By studying how compact galaxy groups interact with the cosmic web, astronomers can gain a better understanding of how galaxies are distributed throughout the universe and how these structures evolve over time. In addition to their role in the cosmic web, compact galaxy groups also provide valuable insights into the behavior of dark matter and dark energy. Dark matter, which makes up about 27% of the universe's mass, and dark energy, which is thought to account for roughly 68% of the universe's energy content, are both essential components of the universe's evolution. While dark matter is known to exert a gravitational pull on galaxies, its exact properties remain largely mysterious. Similarly, dark energy is believed to be responsible for the accelerated expansion of the universe, but its nature is still unknown. Compact galaxy groups, due to their dense environments and interactions with dark matter, provide an ideal setting for studying the behavior of these elusive substances. Through the study of compact galaxy groups, astronomers can learn about the distribution of dark matter within these systems. Dark matter, being invisible, can only be detected through its gravitational effects on visible matter, such as galaxies and gas. By mapping the distribution of galaxies and gas in compact groups, astronomers can infer the location and concentration of dark matter. This can help to shed light on the properties of dark matter and how it interacts with other forms of matter and energy in the universe. Similarly, the study of compact galaxy groups can also provide insights into the influence of dark energy on the evolution of galaxy groups and clusters. The expansion of the universe, driven by dark energy, affects the formation and evolution of large-scale structures, including galaxy groups. Understanding how dark energy influences compact galaxy groups can help astronomers learn more about the fundamental forces that govern the universe. In terms of observational challenges, studying compact galaxy groups at great distances is not without its difficulties. One of the main challenges is the sheer complexity of these systems. Unlike isolated galaxies, which can be studied in relative isolation, compact galaxy groups are dynamic, constantly evolving systems. The galaxies within these groups interact in a variety of ways, from gentle gravitational interactions to violent galaxy collisions and mergers. This makes it difficult to isolate the effects of individual processes and understand how they contribute to the overall evolution of the group. Additionally, compact galaxy groups are often obscured by dust and gas, which can obscure our view of the galaxies within them. To overcome these challenges, astronomers rely on a range of observational techniques, including multi-wavelength observations, gravitational lensing, and sophisticated computer simulations. Multi-wavelength observations are particularly important for studying compact galaxy groups because they allow astronomers to probe different aspects of these systems. For example, observations in the X-ray and radio wavelengths can reveal the properties of the hot, diffuse gas that permeates these groups, while optical and infrared observations can provide detailed images of the galaxies themselves. By combining observations across different wavelengths, astronomers can build a more complete picture of the physical processes occurring within compact galaxy groups and better understand their role in the broader context of galaxy evolution. Gravitational lensing is another powerful tool used to study compact galaxy groups. Gravitational lensing occurs when the gravitational field of a massive object, such as a galaxy group, bends and distorts the light from more distant objects behind it. This effect allows astronomers to study the mass distribution of the galaxy group, including the dark matter that is otherwise invisible. By analyzing the way in which light is bent by the gravitational field of a compact galaxy group, astronomers can gain insights into the distribution of dark matter within the group and better understand its role in shaping the dynamics of the system. In addition to these observational techniques, computer simulations play a crucial role in studying compact galaxy groups. These simulations allow astronomers to model the complex interactions between galaxies and gas in these groups, providing a virtual laboratory for testing different theories about galaxy formation and evolution. By running simulations that incorporate the effects of dark matter, gas dynamics, and galaxy interactions, astronomers can explore a wide range of possible scenarios and test how different processes contribute to the overall evolution of a compact galaxy group. These simulations can also help to predict the behavior of compact galaxy groups in the future, providing valuable insights into how these systems will evolve over time. As we continue to study compact galaxy groups, it becomes clear that these systems offer much more than just a glimpse into the dynamics of individual galaxies. They are a key piece of the puzzle when it comes to understanding the evolution of galaxies and the larger-scale structure of the universe. Through their role in galaxy interactions, their connection to the cosmic web, and their potential to shed light on the mysteries of dark matter and dark energy, compact galaxy groups provide valuable insights into the fundamental processes that shape the universe. Looking ahead, the future of compact galaxy group research is bright. As new telescopes and observational techniques come online, astronomers will be able to study these systems with even greater precision and detail. The upcoming generation of space-based observatories, such as the James Webb Space Telescope, promises to revolutionize our understanding of compact galaxy groups and their role in the evolution of the universe. With continued advancements in technology and the development of new theoretical models, we can expect to uncover even more secrets about these fascinating systems in the years to come. Ultimately, the study of compact galaxy groups is not just about understanding the past or present state of these systems. It is about unlocking the fundamental processes that govern the universe's evolution. By studying the interactions within these small, dense groups of galaxies, we can gain insights into the forces that shape galaxies, the role of dark matter and dark energy, and the evolution of the universe itself. In doing so, we move one step closer to answering some of the most profound questions in cosmology, and gaining a deeper understanding of the vast, interconnected cosmos in which we live. As we continue our exploration of compact galaxy groups, it's important to consider the broader implications of these systems on our understanding of galaxy formation and the large-scale structure of the universe. The study of compact galaxy groups not only gives us a deeper understanding of how galaxies interact and evolve, but also sheds light on the distribution of matter in the universe, the role of dark matter, and the behavior of galaxies in dense environments. In recent years, the role of compact galaxy groups in the formation of galaxy clusters has become a subject of increasing interest. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds to thousands of galaxies. These clusters are the end result of the hierarchical structure formation process, where smaller groups of galaxies merge over time to form larger clusters. Compact galaxy groups, as smaller structures, are thought to play a crucial role in this process by serving as the building blocks of galaxy clusters. When compact galaxy groups merge to form larger structures, the galaxies within these groups can undergo significant transformations. These transformations may involve the stripping of gas from galaxies as they move through the hot, diffuse gas that fills galaxy clusters, as well as the triggering of starbursts or the formation of supermassive black holes at the centers of galaxies. By studying how compact galaxy groups merge to form galaxy clusters, astronomers can gain insights into the processes that govern the growth and evolution of these massive structures and learn more about the fate of galaxies as they become part of larger cosmic systems. Another fascinating aspect of compact galaxy groups is their potential to serve as laboratories for studying the effects of galaxy interactions on star formation. In isolated galaxies, star formation tends to occur in a more regular and predictable manner. However, in compact galaxy groups, the close proximity of galaxies and the frequent interactions between them can lead to a more chaotic and irregular pattern of star formation. The gravitational interactions between galaxies can trigger bursts of star formation, alter the gas content of galaxies, and even cause galaxies to lose their gas, quenching further star formation. These interactions provide an opportunity to study how galaxy collisions and mergers influence the rate of star formation and how these processes contribute to the evolution of galaxies. One intriguing consequence of these interactions is the potential for the creation of tidal dwarf galaxies. Tidal dwarf galaxies are small galaxies that are formed as a result of tidal interactions between two or more larger galaxies. These interactions can cause gas to be stripped from the parent galaxies and form new, small galaxies that are gravitationally bound to one of the larger galaxies. Tidal dwarf galaxies are often found in the outskirts of galaxy groups and are thought to be the result of the same processes that govern the formation of compact galaxy groups. Studying the formation of tidal dwarf galaxies in compact groups can provide valuable insights into the role of galaxy interactions in the creation of new galaxies and the evolution of galaxy populations. In addition to these astrophysical processes, the study of compact galaxy groups also holds potential for advancing our understanding of the cosmic web and large-scale structure. The cosmic web, as previously mentioned, is the vast network of galaxies and dark matter that forms the backbone of the universe's large-scale structure. Compact galaxy groups are often found at the intersections of these cosmic filaments, where galaxies are more densely packed and gravitational interactions are more frequent. By studying the distribution of compact galaxy groups within the cosmic web, astronomers can learn more about how galaxies are distributed across the universe and how the large-scale structure of the universe has evolved over time. The study of compact galaxy groups also offers a unique perspective on the influence of dark matter on galaxy formation. Dark matter is believed to make up about 27% of the universe's mass, yet it cannot be directly observed because it does not emit or interact with light. However, its presence can be inferred through its gravitational effects on visible matter, such as galaxies and galaxy clusters. In compact galaxy groups, the distribution of dark matter plays a crucial role in shaping the dynamics of the system. By mapping the distribution of dark matter in these systems, astronomers can gain valuable insights into its properties and how it interacts with ordinary matter. These studies can also help to improve our understanding of dark matter's role in the formation and evolution of galaxies, clusters, and the larger cosmic web. One of the key challenges in studying compact galaxy groups is the difficulty in observing them in great detail. Unlike individual galaxies, which can be studied in isolation, compact galaxy groups are complex systems that are constantly evolving. Their galaxies interact with one another, exchanging gas, stars, and other materials, which can lead to significant changes in their properties over time. This makes it difficult to disentangle the various processes that govern their evolution and understand how these interactions shape the formation of galaxies and the large-scale structure of the universe. In addition, compact galaxy groups are often obscured by dust and gas, making it difficult to observe the galaxies within them in optical wavelengths. To overcome these challenges, astronomers use a variety of observational techniques, including multi-wavelength observations, gravitational lensing, and computer simulations. Multi-wavelength observations, as mentioned earlier, are particularly useful for studying compact galaxy groups because they allow astronomers to probe different aspects of these systems. By observing compact groups in wavelengths ranging from radio waves to X-rays, astronomers can gain a more comprehensive view of their structure, composition, and behavior. Gravitational lensing is another powerful tool that has been used to study compact galaxy groups. As light from distant objects passes through the gravitational field of a galaxy group, it is bent and distorted, allowing astronomers to study the mass distribution of the group. By analyzing the way in which light is bent by the gravitational field of a compact galaxy group, astronomers can infer the amount and distribution of dark matter within the group. This technique has been instrumental in studying the properties of dark matter and its role in shaping the dynamics of galaxy groups and clusters. Computer simulations also play a crucial role in the study of compact galaxy groups. These simulations allow astronomers to model the interactions between galaxies, gas, and dark matter in these systems. By running simulations that incorporate the physics of galaxy mergers, star formation, and the effects of dark matter, astronomers can explore the behavior of compact galaxy groups and gain insights into the processes that govern their evolution. These simulations also help to predict how compact galaxy groups will evolve over time, providing valuable information about the future of these systems and their role in the larger-scale structure of the universe. As we look to the future, the study of compact galaxy groups will likely continue to be a major focus of astronomical research. With the launch of next-generation telescopes such as the James Webb Space Telescope, astronomers will be able to observe these systems with unprecedented detail and precision. These observations will provide new insights into the formation and evolution of compact galaxy groups, the role of galaxy interactions in shaping the universe, and the mysteries of dark matter and dark energy. As our understanding of these systems grows, so too does our understanding of the universe itself. The study of compact galaxy groups is not just about understanding the dynamics of small, dense clusters of galaxies. It is about unraveling the complex processes that govern the formation and evolution of galaxies, the distribution of matter in the universe, and the fundamental forces that shape the cosmos. By studying these systems, we gain not only a deeper understanding of the universe's past and present but also a glimpse into its future. As we delve deeper into the implications of studying compact galaxy groups, it's essential to explore how these systems provide a glimpse into the mechanisms that govern the universe's large-scale structure and evolution. Compact galaxy groups, with their tightly bound galaxies and intricate interactions, offer an ideal environment for studying the cosmic forces at play on smaller scales. These systems not only reveal the intricate dynamics of galaxy interactions but also allow us to trace the growth of larger structures in the universe, such as galaxy clusters, superclusters, and the cosmic web. The role of compact galaxy groups in galaxy evolution is a subject of particular interest. These systems are often considered cosmic laboratories, where the interplay between gravitational forces, gas dynamics, and dark matter can be studied in ways that aren't possible in more isolated environments. The interactions between galaxies in these groups are far more frequent and violent, leading to a higher rate of galaxy mergers, tidal stripping, and gas exchange. Understanding these interactions can give us insight into the broader mechanisms of galaxy formation and the way in which galaxies evolve over cosmic time scales. In particular, the gravitational interactions between galaxies and compact groups can lead to some extraordinary phenomena. Tidal interactions, for example, are responsible for the creation of tidal tails, long streams of stars, gas, and dust that are stripped from galaxies as a result of gravitational forces exerted by their neighbors. These tidal tails can stretch for hundreds of thousands of light years, and studying them provides valuable clues about the past interactions between galaxies in these groups. Through detailed simulations and observations, astronomers are able to reconstruct the histories of these interactions, piecing together the cosmic puzzle of how galaxies come together, collide, and evolve. Furthermore, the phenomenon of galaxy harassment is particularly significant in the study of compact galaxy groups. In dense environments like these, galaxies experience frequent close encounters with one another, which can have profound effects on their structure and star formation activity. These encounters, known as harassment, can strip galaxies of their gas, leading to the cessation of star formation and the transformation of once active, gas-rich galaxies into passive, gas-depleted ones. This process plays a crucial role in the evolution of galaxy populations, particularly in dense galaxy groups where harassment is more common. Another critical aspect of studying compact galaxy groups is the role of their dense gas reservoirs. Galaxies in these groups often possess significant amounts of intergalactic gas that is heated to high temperatures, making it detectable in X-ray wavelengths. This hot gas plays an essential role in the interactions between galaxies in the group, as it serves as a medium through which energy is exchanged during galaxy collisions. In addition, this gas is often found to be rich in metals, indicating that supernovae explosions and other energetic processes within the galaxies have contributed to the enrichment of the intergalactic medium. The study of this hot, diffuse gas in compact galaxy groups is important because it provides insight into the feedback mechanisms that govern galaxy evolution. For instance, as galaxies merge or experience tidal interactions, the gas within them can be compressed, triggering bursts of star formation. On the other hand, The heating of this gas due to the presence of supermassive black holes at the centers of galaxies or from the interaction between galaxies can quench star formation and turn galaxies into what astronomers call red and dead galaxies. The balance between these two processes, star formation and quenching, depends on a variety of factors, including the mass of the group, the amount of gas present, and the gravitational interactions between the galaxies. One particularly intriguing aspect of compact galaxy groups is their connection to the formation of active galactic nuclei, AGN, and supermassive black holes. Many of the galaxies in these groups are home to supermassive black holes at their centers, and the close proximity of galaxies in the group can cause these black holes to interact with one another. In some cases, the gravitational influence of the black holes can lead to the formation of a binary or even a triple black hole system. These systems are thought to be important for understanding the growth of supermassive black holes and the role that these objects play in regulating the growth of galaxies. The study of AGN in compact galaxy groups has provided significant insights into the mechanisms of black hole growth. When a galaxy undergoes a merger or close interaction, the gas in the galaxy's central region is often funneled toward the supermassive black hole, triggering an outburst of energy in the form of an active galactic nucleus. This energy can take the form of intense radiation across the electromagnetic spectrum, including X-rays, ultraviolet, and radio waves. AGN feedback, which refers to the energy released by these objects, can have profound effects on the surrounding galaxy and its environment, regulating star formation and influencing the distribution of gas and dark matter within the group. This process is particularly significant in compact galaxy groups, where the close proximity of galaxies increases the likelihood of interactions that trigger AGN activity. In these groups, the feedback from AGN can play a crucial role in shaping the evolution of galaxies, helping to explain why some galaxies become quiescent and others continue to form stars at a high rate. Beyond the realm of galaxy interactions, compact galaxy groups also provide valuable insights into the structure of the universe itself. These groups are often found at the intersections of the cosmic web, where the large-scale distribution of galaxies forms a vast, interconnected network. Studying compact galaxy groups at these intersections allows astronomers to investigate the role of dark matter and dark energy in the formation and evolution of galaxies and galaxy clusters. These enigmatic substances, which make up the majority of the universe's mass-energy content, are still poorly understood, but their effects are felt on the largest scales in the universe. The gravitational effects of dark matter are particularly evident in compact galaxy groups. When astronomers observe these groups, they can detect the presence of dark matter through its gravitational influence on the galaxies and the hot gas within the group. This allows them to map the distribution of dark matter in these systems and better understand its role in the formation of galaxies and clusters. Similarly, the study of the large-scale structure of the universe, including the cosmic web, provides important clues about the nature of dark energy and its role in driving the accelerated expansion of the universe. As observational technology continues to advance, astronomers are gaining more detailed and precise data on compact galaxy groups. The advent of the James Webb Space Telescope and next-generation radio observatories will allow for unprecedented observations of these systems, providing more insights into their structure, dynamics, and evolution. These observations will enable astronomers to probe the gas, dark matter, and stellar populations of these groups with greater clarity, opening new doors to understanding how these systems influence the larger-scale structure of the universe. Looking ahead, the study of compact galaxy groups will likely remain a key focus of astrophysical research. These systems provide a window into the complex processes that shape the universe, offering a glimpse into the interactions that govern the growth and evolution of galaxies. They also play a crucial role in understanding the behavior of dark matter, dark energy, and the cosmic web. As our understanding of these systems grows, so too does our understanding of the universe as a whole. Through the study of compact galaxy groups, we are not only learning about the interactions and evolution of galaxies but also uncovering the fundamental processes that govern the large-scale structure of the cosmos. These small, dense groups of galaxies serve as laboratories where the laws of gravity, gas dynamics, and dark matter can be tested in extreme conditions. The lessons we learn from these systems will ultimately help to shape our understanding of the universe, its origins, and its future. The study of compact galaxy groups is evolving rapidly as new observational technologies and more sophisticated simulations become available. As mentioned earlier, compact galaxy groups, like Stephan's Quintet, provide valuable insights into the ways galaxies interact within a dense environment. These groups offer unique opportunities to study various astronomical phenomena that would be difficult or impossible to observe in more isolated galaxies. For instance, compact galaxy groups are ideal environments for investigating galaxy mergers and the interactions between galaxies and dense, highly gravitationally bound systems. Galaxies within these groups frequently undergo close encounters that result in physical exchanges of stars, gas, and dust. These interactions can lead to the formation of tidal tails, vast streams of material that are pulled from galaxies as a result of gravitational interactions. Tidal stripping, where a galaxy loses parts of its outer stellar envelope, is a key process that plays out in these dense regions. These stripped stars and gas clouds give us crucial insight into the strength and nature of the gravitational forces at play in the compact group environment. In some cases, the interactions between galaxies and compact groups can also trigger the formation of star clusters. When two or more galaxies collide, their gas clouds can compress and trigger bursts of star formation, leading to the creation of new generations of stars. This phenomenon, known as starburst activity, is particularly prevalent in compact galaxy groups, where the close proximity of galaxies ensures that interactions are frequent enough to cause such events. Understanding how starbursts occur in these environments, and their subsequent impact on galaxy evolution is an area of intense study. The high density of compact galaxy groups also means that they provide an excellent setting for observing the role of active galactic nuclei, AGN, in galaxy evolution. Many of the galaxies in these groups contain supermassive black holes at their centers, and the gravitational interactions in these dense environments often lead to the activation of these black holes. As galaxies merge or come into close proximity, the gas at the center of the galaxy can be funneled toward the black hole, feeding it and causing it to shine brightly as an AGN. AGNs are among the most energetic phenomena in the universe, and their study in compact galaxy groups can help us understand not only the growth of supermassive black holes but also how AGNs influence the surrounding galaxies and their environments. Feedback from AGNs is a crucial component of galaxy evolution in compact groups. The energy output from AGNs can have a profound impact on the surrounding gas, often heating it to millions of degrees and preventing it from cooling and forming new stars. This process, known as AGN feedback, can inhibit star formation in galaxies and lead to their transformation into red and dead galaxies. These galaxies, once rich in gas and active in star formation, become passive and redder in color as they run out of the cold gas needed for star formation. Understanding the role of AGN feedback in compact galaxy groups is crucial for our broader understanding of galaxy formation and evolution. Another intriguing aspect of compact galaxy groups is the role that dark matter plays in shaping their structure and dynamics. While dark matter cannot be directly observed, its presence is inferred through its gravitational effects on visible matter. In compact galaxy groups, dark matter is believed to account for a significant portion of the total mass in the system. By studying the motion of galaxies and the hot gas within these groups, astronomers can map the distribution of dark matter and gain insights into its properties. For instance, the way in which galaxies and compact groups are bound together by dark matter can provide valuable information about the nature of this mysterious substance and its role in the formation of galaxies. The study of dark matter in compact galaxy groups has implications for understanding the larger-scale structure of the universe. The distribution of dark matter in these groups can help astronomers trace the growth of cosmic structures such as galaxy clusters and superclusters. Compact galaxy groups are often seen as the building blocks of larger systems, and studying their dark matter content is crucial for understanding the evolution of the universe as a whole. Dark matter's influence on galaxy formation and clustering is central to current cosmological models, and compact galaxy groups offer a unique opportunity to test these models in environments that are both dense and dynamic. Moreover, compact galaxy groups are often located at the intersections of the cosmic web, a vast network of galaxies and dark matter that stretches across the universe. The cosmic web consists of vast filaments of galaxies and dark matter that connect galaxy clusters and superclusters, forming a large-scale structure that resembles a spiderweb. Compact galaxy groups, with their dense galaxies and dark matter, are located at these intersections, where the filaments of the cosmic web meet. Studying the dynamics of these groups helps astronomers understand how galaxies are distributed across the universe and how they are influenced by the large-scale structure of the cosmos. In addition to their role in galaxy formation and dark matter studies, compact galaxy groups are also valuable in the search for clues about the evolution of the universe's large-scale structure. These systems are often found in regions where the cosmic web is densest, making them key players in the development of the universe's structure. By studying how compact galaxy groups evolve over time, astronomers can gain insights into the forces that have shaped the distribution of galaxies across the cosmos. An important aspect of compact galaxy groups is their connection to the broader universe's history. The processes occurring in these groups, galaxy mergers, interactions, and the growth of supermassive black holes, are not only relevant to the study of local systems, but also provide important clues about the evolution of the universe as a whole. Compact galaxy groups serve as snapshots of galaxy evolution at different stages of cosmic history, and by studying these systems, we can reconstruct the story of how galaxies have formed and evolved over billions of years. One of the most fascinating aspects of compact galaxy groups is how they mirror the early universe's conditions. These groups often resemble the environments that existed shortly after the formation of the first galaxies, providing a unique opportunity to study galaxy evolution in its early stages. As such, compact galaxy groups can be seen as analogues to the primordial universe, offering a glimpse into the processes that led to the formation of galaxies and larger cosmic structures. By studying these groups, astronomers can better understand the conditions that led to the creation of the first galaxies and how they evolved into the systems we observe today. The ongoing observation of compact galaxy groups continues to shed light on these and other critical aspects of cosmic evolution. As new telescopes and instruments come online, such as the James Webb Space Telescope and next-generation radio observatories, our understanding of compact galaxy groups will only deepen. These advancements will allow us to peer even further into the heart of these systems, revealing more about the gas, stars, and dark matter that comprise them. In the future, we may even uncover entirely new phenomena that will reshape our understanding of the cosmos. The study of compact galaxy groups offers an invaluable perspective on the processes that shape the universe. These small, dense collections of galaxies serve as cosmic laboratories, where we can study the interactions that govern galaxy evolution, the role of dark matter, the growth of supermassive black holes, and the dynamics of the cosmic web. The insights gained from studying these systems will continue to inform our understanding of the universe's past, present, and future. As our observational tools improve and our understanding of galaxy groups deepens, we are bound to uncover even more about these fascinating cosmic structures, enriching our knowledge of the universe and our place within it. Compact galaxy groups represent some of the most exciting and complex regions of the universe, providing an intricate window into the interaction and evolution of galaxies under extreme conditions. These groups are much smaller in scale compared to the larger galaxy clusters, but their dense environments give rise to a wide range of physical processes that are not easily observed in isolated galaxies. Their role in the larger framework of cosmology and galaxy formation cannot be overstated, and there is still much to learn about how galaxies behave in these crowded, gravitationally intense regions. When studying compact galaxy groups like Stephan's Quintet, astronomers gain insight into the processes that drive galaxy formation in the early universe. The interaction between galaxies in such groups provides clues about the evolution of galactic structures over cosmic time. These groups serve as test beds for theories of galaxy formation and evolution, as they allow scientists to observe galaxy mergers, the stripping of gas, the fueling of supermassive black holes, and the impact of dark matter in real time. For instance, one of the key phenomena that occurs in these dense environments is galaxy merging. The process of two or more galaxies merging can lead to significant changes in their structure, star formation activity, and central black hole dynamics. During a merger, the gravitational forces between the galaxies cause their gas clouds to collide and compress, triggering bursts of star formation and potentially feeding the central supermassive black hole. These mergers can result in the formation of elliptical galaxies, which are typically the end product of multiple galactic collisions. As galaxies lose their gas and dust through these interactions, they often evolve from actively star-forming spiral galaxies to more passive, redder elliptical galaxies. Studying these mergers in compact galaxy groups provides crucial information about the later stages of galaxy evolution and the dynamics that govern these transformations. The central supermassive black holes in these galaxies are also a focal point of research in compact groups. As galaxies interact, their central black holes often experience significant changes in their feeding behavior. The close proximity of galaxies can funnel gas toward these black holes, feeding them and causing them to shine brightly as active galactic nuclei, AGN. These AGNs release vast amounts of energy, which can have a profound impact on their surrounding environments. The energy output from AGNs can heat up the surrounding gas, prevent it from cooling, and suppress star formation in the host galaxy, a phenomenon known as AGN feedback. Understanding how AGNs influence galaxy evolution in compact groups is key to understanding how galaxies transition from active, star-forming systems to more passive ones. At the same time, the study of the hot gas in compact galaxy groups offers another crucial piece of the puzzle. Many compact groups are surrounded by diffuse gas that is heated to millions of degrees due to the gravitational interactions between galaxies. This hot gas, which emits X-rays, can be detected by space telescopes, allowing scientists to study the distribution and dynamics of the gas within the group. The gas in these groups is also often influenced by the central supermassive black holes, which can inject energy into the gas through AGN feedback. The study of this gas provides valuable information about the state of the intergroup medium and the processes that regulate star formation and galaxy evolution. Dark matter, the invisible substance that makes up most of the mass in the universe, is also a key player in the dynamics of compact galaxy groups. While dark matter cannot be directly observed, its presence is inferred through its gravitational effects on visible matter. In compact galaxy groups, dark matter is believed to be responsible for holding the galaxies together, providing the gravitational binding that keeps them from flying apart. By studying the motion of galaxies within compact groups, astronomers can map the distribution of dark matter and gain insights into its properties. The distribution of dark matter in these groups can also help astronomers understand the larger-scale structure of the universe, as compact galaxy groups are often located at the intersections of the cosmic web, the vast network of galaxies and dark matter that forms the backbone of the universe. The study of dark matter in compact galaxy groups is also essential for testing our current models of cosmology. The interaction between dark matter and ordinary matter in these groups provides a unique opportunity to probe the nature of dark matter and its role in galaxy formation. By observing how galaxies in compact groups move and interact, scientists can place constraints on the properties of dark matter and test different hypotheses about its composition. Some researchers speculate that dark matter may be made up of exotic particles, such as weakly interacting massive particles, WIMPs, or axions. Others believe that dark matter could be made up of primordial black holes. The study of dark matter in compact galaxy groups is helping to shape the ongoing search for these elusive particles and further our understanding of the universe's most mysterious component. Moreover, compact galaxy groups also provide an opportunity to study the role of gas and dust in galaxy evolution. In isolated galaxies, gas and dust are crucial components for star formation. However, in compact galaxy groups, the interactions between galaxies can strip away gas and dust, leaving galaxies with little fuel to form new stars. This process, known as ram pressure stripping, occurs when a galaxy passes through the hot gas that fills the space between galaxies in a group. The gas exerts pressure on the galaxy, stripping away its outer gas and dust layers, which can prevent star formation. In some cases, this process can even remove all of a galaxy's gas, effectively shutting down its ability to form new stars. Studying RAM pressure stripping in compact galaxy groups provides insight into the processes that regulate star formation in galaxy groups and clusters, and helps astronomers understand how galaxies evolve over time. The impact of the surrounding environment on galaxy evolution is a key theme in the study of compact galaxy groups. Unlike isolated galaxies, which evolve relatively independently, galaxies in compact groups are subject to a wide range of environmental factors that can accelerate or inhibit their evolution. The high density of galaxies in compact groups means that galaxies are frequently interacting with one another, leading to a greater frequency of mergers, tidal interactions, and gas stripping events. These interactions can lead to a variety of outcomes, from the formation of new stars to the destruction of galaxy structures. By studying compact galaxy groups, astronomers can better understand how the environment shapes the evolution of galaxies and the broader processes of galaxy formation and transformation. Compact galaxy groups also play a crucial role in understanding the large-scale structure of the universe. These groups are often located in regions where the cosmic web, the vast network of galaxies and dark matter, intersects. The study of these groups helps astronomers understand how galaxies are distributed across the universe and how they are influenced by the large-scale cosmic structure. As the universe continues to evolve, compact galaxy groups may merge and grow into larger galaxy clusters, further shaping the distribution of galaxies and dark matter in the cosmos. Understanding the formation and evolution of these groups provides crucial insight into the forces that govern the structure of the universe. The study of compact galaxy groups is a vital area of research in astrophysics, offering valuable insights into galaxy evolution, the role of dark matter, the dynamics of galaxy mergers, and the influence of AGNs and gas on galactic environments. These dense, interactive systems provide a unique laboratory for studying the complex processes that govern galaxy formation and evolution. As our observational tools continue to improve, our understanding of these systems will only deepen, offering new clues about the nature of the universe and the forces that shape it. Compact galaxy groups, especially those like Stephan's Quintet, remain a critical focus of astrophysical research due to their complex interactions and unique characteristics. As we continue to delve into the mysteries of these cosmic environments, the intricate mechanisms driving their evolution unfold with greater clarity, bringing new insights into the processes that govern the birth, growth, and eventual transformation of galaxies. To understand the full scope of these interactions, it's important to consider the dynamics at play within a compact galaxy group. Unlike isolated galaxies or more loosely bound galaxy clusters, compact groups are defined by their high galaxy density. The galaxies within these groups are in such close proximity to one another that their gravitational influence on each other becomes a key factor in their evolution. In fact, the mutual interactions between these galaxies, whether through direct collisions, tidal forces, or other means, are at the heart of the processes that shape their future. One particularly intriguing aspect of compact galaxy groups is the phenomenon of galaxy harassment. Galaxy harassment refers to the high-frequency gravitational interactions that occur when galaxies within a group pass closely by each other. These interactions can disrupt the structure of the galaxies, particularly their stellar and gas components. As a result, galaxy harassment can induce star formation, alter the galaxy's shape, or even cause the stripping of gas and dust from the galaxy. This ongoing process significantly accelerates the transformation of galaxies, driving their evolution in ways that wouldn't occur in isolation. Moreover, this chaotic environment often leads to the depletion of the galaxy's gas, which can halt star formation. This is particularly evident in what we call starbursts, intense periods of star formation that are triggered by interactions within the group. As gas clouds collide during a close encounter, they compress, triggering waves of new stars. However, once the gas is used up or stripped away through these interactions, the galaxy's ability to produce new stars diminishes, and it eventually becomes a more passive, red-ended elliptical galaxy. The role of supermassive black holes in compact galaxy groups cannot be overlooked. These powerful engines at the centers of galaxies are often influenced by the surrounding environment. In compact groups, the presence of multiple galaxies means that the central supermassive black holes may not evolve in isolation. Instead, their growth can be directly impacted by interactions with neighboring galaxies. When two galaxies collide or pass close to one another, the black holes at their centers may eventually merge, resulting in the formation of even more massive black holes. These mergers can also release enormous amounts of energy in the form of gravitational waves and electromagnetic radiation, providing astronomers with an opportunity to study these cosmic events in greater detail. In some cases, the activity of supermassive black holes can contribute to feedback mechanisms that affect the group as a whole. This feedback, particularly in the form of AGN-driven winds or jets, can disrupt the gas in the group, preventing it from cooling and forming new stars. This process is an essential part of regulating star formation within these environments. While these black holes can serve as powerful agents of change, they also highlight the delicate balance between gravitational forces, gas dynamics, and the overall evolution of the group. Another fascinating element of compact galaxy groups is the presence of intragroup gas. In contrast to the gas found within individual galaxies, this gas exists in the space between galaxies, often referred to as the intragroup medium. It is primarily heated to millions of degrees due to the gravitational interactions within the group. This gas can be observed using X-ray telescopes, providing valuable data on the distribution and temperature of the hot gas in these dense regions. The dynamics of this intragroup gas are crucial for understanding the overall energy balance within the group and its role in the evolution of the galaxies. Interestingly, the hot intragroup gas can also provide insights into the presence and distribution of dark matter. While dark matter cannot be observed directly, its gravitational effects can be inferred from the behavior of visible matter, such as the movement of galaxies and the distribution of gas. In compact galaxy groups, the gravitational influence of dark matter helps to keep the group's galaxies bound together. By studying the motion of galaxies within these groups and the behavior of the gas, astronomers can map the dark matter distribution, offering valuable insights into the nature of this mysterious component of the universe. Over time, the interactions within compact galaxy groups lead to a gradual but inevitable transformation. As galaxies merge, their stars and gas are redistributed, and new structures can form. Some galaxies may become isolated, while others may form more tightly bound systems. The resulting mergers and interactions also contribute to the larger-scale structure of the universe, as compact groups eventually grow and merge into larger galaxy clusters. In this way, compact galaxy groups serve as an essential step in the cosmic evolution of galaxy structures, contributing to the formation of the massive clusters that dominate the large-scale universe. The study of compact galaxy groups is also crucial for understanding the processes that occur in the early universe. In the distant past, the universe was much smaller and more densely packed with galaxies. As the universe expanded, galaxies began to move away from each other, but not all galaxies were affected equally. Some were bound together in small, dense groups, where the interactions and processes we observe in compact galaxy groups today would have been more common. By studying these systems, astronomers can gain a better understanding of the conditions that existed in the early universe and how they led to the formation of the galaxies we see today. As our observational tools improve, the study of compact galaxy groups will continue to yield new discoveries. For example, the advent of advanced space telescopes, such as the James Webb Space Telescope, will allow astronomers to peer deeper into the universe than ever before. This will enable scientists to study the most distant and earliest compact galaxy groups, providing a clearer picture of how galaxies interacted and evolved in the early stages of the universe's history. With such powerful tools at our disposal, we can expect to uncover more details about the role of compact galaxy groups in shaping the universe as a whole. In addition to their scientific value, compact galaxy groups also offer a captivating glimpse into the dynamic and ever-changing nature of the universe. The interactions between galaxies, black holes, gas, and dark matter in these groups represent some of the most fundamental processes driving cosmic evolution. By studying these systems, we can better understand the forces that govern the universe and our place within it. The compact galaxy groups may be small in scale, but their importance in the grand scheme of the cosmos is immeasurable. As we continue to investigate the mysteries of these unique environments, we will undoubtedly unlock even more secrets about the universe's past, present, and future. From the birth of new stars to the merging of galaxies and the growth of supermassive black holes, the study of compact galaxy groups offers us an unparalleled opportunity to observe the fundamental processes that shape our universe. And as we delve deeper into the vastness of space, one thing is certain: there will always be more to discover. As we move further into understanding the intricacies of compact galaxy groups, it's essential to take a moment to reflect on the bigger picture. The formation of these dense cosmic systems represents one of the most captivating phenomena in astrophysics. Compact galaxy groups are the epitome of cosmic interactions, where galaxies are not merely passive objects in space, but rather active participants in a symphony of gravitational forces, gas dynamics, and energy exchanges. Every interaction, from a simple close encounter to a full-blown merger, leaves behind an indelible mark on the group's overall structure, and this, in turn, contributes to the broader evolutionary processes of the universe. One of the standout features of compact galaxy groups is the long-term impact of galaxy mergers. These events, where galaxies collide and combine, are critical for understanding the evolution of galaxies themselves. Over billions of years, galaxy mergers reshape the constituent galaxies. In some cases, smaller galaxies can be absorbed by a more massive one, effectively ceasing to exist as independent entities. This process leads to the formation of new galaxy types, such as elliptical galaxies, which often arise from the violent merger of spiral galaxies. These elliptical galaxies, characterized by their smooth, featureless structure, are often the end product of multiple galactic collisions. The role of galactic interactions and mergers in driving star formation is another fascinating aspect of compact galaxy groups. During a merger, gas clouds within the interacting galaxies collide, compressing under the immense gravitational forces. This compression triggers bursts of star formation known as starbursts. The intensity of these bursts depends on the nature of the interaction. In some cases, the collision may lead to a rapid and violent burst of star formation, while in other instances, the galaxies may experience a more gradual process. These starbursts play a crucial role in shaping the future of the galaxy, often leading to the formation of new, young stars that add to the galaxy's population. However, the aftermath of these intense interactions often comes with consequences. The energy released during a merger, especially in the form of supernovae and other violent astrophysical phenomena, can expel gas and dust from the galaxy. This process, known as feedback, can prevent the galaxy from forming new stars, as the expelled gas is no longer available for star formation. This interplay between star formation and gas expulsion is one of the key mechanisms that regulate the growth and evolution of galaxies. In the case of compact galaxy groups, the interaction between galaxies and their environment is even more complex. The gravitational influence exerted by neighboring galaxies can cause significant distortions in the structure of individual galaxies. Tidal forces, for instance, can stretch and pull at the outer regions of a galaxy, distorting its shape and even stripping away gas and stars. This phenomenon, known as tidal stripping, can significantly alter the galaxy's morphology and star formation history. Over time, this can lead to the transformation of a once spiral galaxy into a more passive elliptical galaxy, devoid of the gas needed for continued star formation. Another key factor in the evolution of compact galaxy groups is the role of dark matter. Dark matter, the mysterious and invisible substance that makes up a significant portion of the universe's mass, plays a crucial role in the gravitational dynamics of compact galaxy groups. While dark matter cannot be directly observed, its presence can be inferred by observing the gravitational effects it has on visible matter, such as galaxies and gas clouds. In compact groups, dark matter helps to bind the galaxies together, ensuring that they remain in close proximity despite the intense gravitational interactions that occur within these groups. By studying the distribution of dark matter in compact galaxy groups, astronomers can gain valuable insights into its properties and behavior, helping to unravel one of the most profound mysteries of modern astrophysics. The study of compact galaxy groups also provides important clues about the large-scale structure of the universe. These small, dense groups are the building blocks of the larger galaxy clusters that populate the universe. Understanding how compact groups evolve and merge can offer valuable insights into the formation and growth of these larger structures. As compact groups collide and merge over time, they contribute to the larger-scale formation of galaxy clusters, which are some of the most massive structures in the universe. These clusters, in turn, play a critical role in the cosmic web, the vast network of galaxies and dark matter that stretches across the universe. Moreover, compact galaxy groups serve as natural laboratories for studying the effects of environment on galaxy evolution. In the early universe, compact groups were far more common, as galaxies were much more closely packed together. Over time, as the universe expanded and galaxies moved apart, these groups became less frequent. However, the study of these ancient, dense systems offers a unique opportunity to understand the processes that shaped the early universe and how they contributed to the formation of the galaxies we observe today. By studying the interactions and transformations occurring within compact galaxy groups, astronomers can gain insights into the conditions that existed in the early stages of the universe's history. Looking forward, the study of compact galaxy groups will continue to evolve as new observational tools and techniques become available. The advent of more powerful telescopes, both ground-based and space-based, will allow astronomers to probe these systems with unprecedented detail. Instruments like the James Webb Space Telescope, which is capable of observing distant galaxies and compact groups in infrared light, will provide new opportunities to study the formation and evolution of galaxies in these dense environments. Additionally, advancements in computational simulations will enable researchers to model the complex dynamics of galaxy interactions within compact groups, offering even deeper insights into the processes at play. As we continue to explore these cosmic systems, the importance of compact galaxy groups in our understanding of the universe cannot be overstated. These dense, highly interactive environments provide a window into the fundamental processes that shape galaxies, star formation, and the larger-scale structure of the cosmos. Whether through direct observations or advanced simulations, the study of compact galaxy groups offers a unique and invaluable perspective on the universe's past, present, and future. In many ways, compact galaxy groups are microcosms of the larger cosmic processes that govern the evolution of the universe. Within these small, dense regions, galaxies are born, evolve, merge, and transform, driven by a complex interplay of gravitational forces, gas dynamics, and dark matter interactions. By studying these systems, we can better understand the forces that shape galaxies and the larger structures of the universe. As our observational techniques improve and our understanding deepens, the mysteries of compact galaxy groups will continue to captivate astronomers, providing us with crucial insights into the nature of the universe itself. As we venture deeper into the study of compact galaxy groups, it becomes evident that these systems offer an exceptional opportunity to explore the complexities of the universe's most dynamic and transformative processes. The intricate interactions between galaxies, their gas, and dark matter create a cosmic laboratory where astrophysical phenomena unfold on timescales that span billions of years. Understanding the role of compact galaxy groups in the cosmic narrative will not only help us comprehend how galaxies form and evolve, but it will also allow us to probe deeper questions about the nature of space-time, dark matter, and the universe's ultimate fate. One key feature that sets compact galaxy groups apart from other galaxy systems is their dense concentration of galaxies. Unlike galaxy clusters, which can host hundreds or even thousands of galaxies scattered across vast expanses of space, compact galaxy groups are much smaller in scale but more tightly bound. Typically, these groups consist of just a few to several dozen galaxies that are packed closely together. This high galaxy density creates a very different environment compared to the more diffuse regions of the universe. The intense gravitational interactions between galaxies in these groups lead to a variety of fascinating phenomena, including tidal forces, galaxy mergers, and the stripping of gas from galaxies. All of these effects contribute to the dramatic evolution of the group as a whole, as well as to the individual fates of the galaxies involved. One of the most striking outcomes of these interactions is the transformation of galaxy morphology. In these compact systems, galaxies undergo significant changes, particularly when they experience close encounters with one another. The gravitational forces at play can distort the shape of a galaxy, pulling its stars and gas into elongated structures or even triggering the collapse of gas clouds. This process, called tidal disruption, can result in dramatic changes in the appearance of a galaxy. Some galaxies may lose their characteristic spiral arms, while others may be stretched out into long, thin shapes. In extreme cases, entire galaxies may be torn apart and absorbed into larger, more massive galaxies. These transformations are not only visually striking, but they also provide critical insights into the forces that govern galaxy formation and evolution. Tidal stripping, another crucial phenomenon in compact galaxy groups, plays an important role in shaping the fate of galaxies in these dense environments. During a close encounter, the gravitational pull of one galaxy can strip away the gas and stars from another galaxy. This process can significantly alter the galaxy's ability to form new stars, as the loss of gas leaves the galaxy with little fuel for star formation. Tidal stripping is particularly important in compact groups because of the relatively small size of the system. In such a dense environment, close encounters between galaxies are more frequent, and the gravitational interactions are stronger. As a result, galaxies in compact groups are more likely to lose their gas and undergo morphological changes, potentially turning them from star-forming spirals into more passive elliptical galaxies. While these processes of transformation and disruption are fascinating, they also offer a window into the broader dynamics of the universe. By studying the behavior of galaxies within compact galaxy groups, astronomers can gain valuable insights into the long-term evolution of galaxies and clusters. These insights can help us understand how galaxies grow, how they interact with their surroundings, and how they contribute to the formation of larger structures like galaxy clusters. In a sense, compact galaxy groups can be thought of as miniature versions of galaxy clusters, with each group representing a different stage in the larger cosmic process. The impact of dark matter on the formation and evolution of compact galaxy groups is another area of intense study. Dark matter, which accounts for a significant portion of the universe's mass, is thought to play a key role in the gravitational interactions that occur in these systems. While dark matter cannot be directly observed, its presence can be inferred from its gravitational effects on visible matter. In compact galaxy groups, the presence of dark matter helps to stabilize the system and keep the galaxies bound together. Without dark matter, the gravitational pull from the galaxies themselves would not be enough to prevent them from flying apart. As such, the study of compact galaxy groups provides an important opportunity to investigate the nature of dark matter and its role in the formation of galaxy systems. The role of gas within compact galaxy groups is also crucial in understanding their evolution. Gas is the primary fuel for star formation, and it plays an important role in shaping the fate of galaxies. However, in compact groups, the intense gravitational interactions between galaxies can cause significant changes in the distribution and state of gas. In some cases, gas may be stripped from a galaxy during a close encounter, leaving the galaxy without the raw materials needed to form new stars. In other cases, the gas may be compressed and heated, leading to the formation of new stars. These gas dynamics are essential to understanding how galaxies evolve over time, and how they contribute to the larger processes of cosmic evolution. The process of star formation itself is another area of interest when studying compact galaxy groups. During galaxy interactions, gas clouds within the galaxies can be compressed by gravitational forces, triggering bursts of star formation. These starbursts can be particularly intense in compact groups, as the galaxies are much more likely to experience close encounters. Starbursts play a key role in shaping the population of stars within a galaxy and can lead to the formation of young, massive stars. However, star formation can also be suppressed in some cases due to feedback from active galactic nuclei, AGN. The intense radiation and outflows from an AGN can expel gas from the galaxy, preventing further star formation. This delicate balance between star formation and suppression is a key factor in the evolution of galaxies in compact groups. While the study of compact galaxy groups has already revealed a wealth of information, there is still much to learn. As observational technology continues to improve, new discoveries will be made that further illuminate the behavior of these fascinating systems. For example, the upcoming launch of the James Webb Space Telescope promises to offer unprecedented views of distant galaxies and compact groups, providing valuable data that will help refine our understanding of galaxy evolution. Additionally, the continued development of computational simulations will enable researchers to model the interactions and dynamics of galaxy groups with even greater accuracy. The study of compact galaxy groups is a crucial piece of the puzzle in understanding the evolution of galaxies and the large-scale structure of the universe. These dense, highly interactive systems provide valuable insights into the processes that shape galaxies, from tidal forces and galaxy mergers to the role of gas and dark matter. By continuing to explore these cosmic laboratories, we can gain a deeper understanding of the forces that govern the universe and how they have shaped the galaxies we see today. As our understanding of compact galaxy groups grows, so too does our understanding of the universe itself, revealing a more complete picture of the cosmic processes that have shaped the cosmos over billions of years. As we continue to explore compact galaxy groups, we cannot ignore the intricate relationship between galaxy dynamics and the environment in which they reside. The dense environments of these groups significantly affect their galaxies, and understanding these relationships is crucial for grasping the larger picture of cosmic evolution. The interplay between galaxy interactions, dark matter, and gas dynamics in compact groups paints a picture of a highly dynamic and ever-changing universe. Every galaxy in these groups has a story, one shaped by the forces of gravity, dark matter, and radiation, all of which leave lasting marks on their evolution. One of the most fascinating aspects of studying compact galaxy groups is their ability to shed light on the processes that influence galaxy morphology. In these tight-knit systems, galaxies are much more likely to experience interactions that alter their structure. Unlike the more isolated galaxies we observe in less dense regions of the universe, galaxies within compact groups are exposed to frequent gravitational encounters with other galaxies. These interactions can have profound effects, ranging from minor distortions in shape to the complete merger of galaxies. A classic example of this process can be observed in Stephan's Quintet, a well-known compact galaxy group. In this group, the galaxies are involved in a complex series of gravitational interactions that have significantly altered their original shapes and structures. One galaxy in the group, for instance, is undergoing a dramatic tidal disruption, with its gas and stars being stretched out into long, thin structures. These dramatic changes serve as a powerful reminder of how gravitational interactions can reshape galaxies over time. Galaxy mergers, a common result of the close encounters in compact groups, are another key feature of these systems. When two galaxies collide, their individual stars rarely collide with one another due to the vast distances between stars. However, the gravitational forces at play can have significant effects on the gas and dust within the galaxies. As the galaxies merge, their gas clouds can collide, compressing the gas and triggering new waves of star formation. This process, known as a starburst, can lead to the formation of large numbers of new stars in a relatively short period of time. These starbursts are often accompanied by the formation of massive star clusters and sometimes even the birth of supermassive black holes in the cores of the newly merged galaxies. However, mergers can also have destructive consequences. The interaction between galaxies can lead to the stripping of gas from one or both of the galaxies, a process known as ram pressure stripping. This occurs when the gas in a galaxy is pushed out of the galaxy due to the high-speed motion through the hot, diffuse gas in the intergalactic medium. Without its gas, a galaxy is unable to form new stars, leading to a gradual fading of its stellar population. Over time, this can transform a once vibrant star-forming galaxy into a quiescent elliptical galaxy. The fate of such galaxies can be further influenced by the presence of an active galactic nucleus, AGN, in one of the merging galaxies. The intense radiation and outflows from an AGN can expel gas from the galaxy, further suppressing star formation and contributing to the transformation of the galaxy. While tidal interactions and mergers are crucial components of the evolution of galaxies in compact groups, they are not the only forces at work. The presence of dark matter is also a fundamental aspect of these systems. Dark matter, an invisible and mysterious substance that does not interact with light, is thought to make up a significant portion of the mass in these groups. Though it cannot be directly observed, dark matter's presence can be inferred from its gravitational effects on visible matter. In the case of compact galaxy groups, the gravitational pull of dark matter helps to bind the galaxies together, preventing them from flying apart due to their mutual gravitational attraction. Without dark matter, the galaxies in these groups would not be able to remain in such close proximity to one another. Dark matter also plays a role in the overall dynamics of the group, influencing how the galaxies move and interact with one another. One important aspect of dark matter's role in compact galaxy groups is its potential influence on the formation of the group itself. While galaxy groups are thought to form through the gradual accumulation of galaxies, the presence of dark matter may speed up this process. Dark matter clumps together in the early universe, forming structures that act as gravitational wells for ordinary matter to fall into. As galaxies form and interact with one another, dark matter can help guide their motion and facilitate the growth of compact groups. In this way, dark matter not only plays a critical role in maintaining the stability of these groups but also in their very creation. Another key feature of compact galaxy groups is the role that gas plays in shaping their evolution. Gas is the primary ingredient for star formation, and the behavior of gas in these groups is crucial for understanding how galaxies evolve. In some cases, the gas within a galaxy may be stripped away during a close encounter, leaving the galaxy with little to no fuel for star formation. This process, known as gas stripping, is a significant factor in the quenching of star formation in galaxies and compact groups. Without access to new gas, a galaxy may eventually run out of the raw materials needed to form new stars, leading to the cessation of star formation. In other cases, however, the gas in a galaxy may be compressed during a close encounter, triggering a burst of star formation. This process, known as a starburst, can lead to the formation of massive new stars in a relatively short amount of time. The interactions between gas, stars, and dark matter in compact galaxy groups create a complex and dynamic environment in which galaxies evolve. Over time, these interactions can lead to the transformation of galaxies from star-forming spirals into more passive elliptical galaxies. However, the precise mechanisms that drive these transformations are still not fully understood. Some researchers believe that the key to understanding this process lies in the study of the gas within compact groups. By observing the behavior of gas in these systems, astronomers hope to gain new insights into how galaxies evolve over time and how they are shaped by their environment. In the larger context of the universe, the study of compact galaxy groups is crucial for understanding the evolution of galaxy clusters and the large-scale structure of the cosmos. Compact galaxy groups are often seen as the building blocks of larger systems, such as galaxy clusters. By studying the dynamics of these smaller groups, astronomers can gain a better understanding of how galaxy clusters form and evolve over time. The study of compact groups can also shed light on the role of dark matter in the formation of large-scale structures in the universe. As these groups merge and interact, they contribute to the growth of larger structures, providing a glimpse into the forces that shape the universe on the grandest scales. The upcoming generation of telescopes and observatories will provide new insights into the nature of compact galaxy groups. The James Webb Space Telescope, for instance, promises to offer unprecedented views of distant galaxies and compact groups, allowing researchers to study their dynamics in greater detail. Additionally, the continued development of computational simulations will enable astronomers to model the interactions and evolution of galaxy groups with increasing accuracy. These advancements in observational and computational techniques will undoubtedly lead to new discoveries, further enriching our understanding of these fascinating cosmic systems. Compact galaxy groups are key to unlocking many of the mysteries surrounding galaxy formation, evolution, and the nature of the universe itself. These dense, dynamic systems offer a unique glimpse into the forces that shape galaxies and their environments, from tidal interactions and gas dynamics to the role of dark matter in their stability. As we continue to study compact galaxy groups, we will undoubtedly uncover new insights into the processes that govern the cosmos, offering a deeper understanding of the universe and its evolution. As we continue our exploration of compact galaxy groups, it's essential to understand how these environments offer a laboratory for the study of cosmic evolution on a smaller scale. When we zoom in on these dense clusters of galaxies, we're not just witnessing the evolution of individual galaxies, but rather the interactions and dynamics that occur within the broader fabric of the universe. Compact galaxy groups act as microcosms, revealing processes that, over time, contribute to the larger-scale evolution of galaxy clusters and, ultimately, the entire cosmos. In the heart of these dense groups, the mutual gravitational attraction between galaxies leads to an intricate web of forces. The gravitational pull within a compact galaxy group is intense. It's not just the individual galaxies themselves that feel this pull. The dark matter that permeates the entire region contributes significantly to the gravitational effects. The result is a finely tuned interaction between the galaxies, dark matter, and gas. As galaxies interact, they experience forces that can distort their shape, trigger bursts of star formation, and sometimes even lead to the merger of galaxies. A striking example of such interaction can be seen in Stephan's Quintet, one of the most famous compact galaxy groups in the universe. Composed of 5 galaxies, 4 of which are in close proximity to one another, Stephan's Quintet is a dynamic example of galaxy collision and interaction. The gravitational forces at play within this group are so intense that they cause distortions in the galaxies themselves, including long tidal tails and bridge-like structures of stars and gas that stretch between them. These tidal features are a direct result of the interactions, providing a dramatic visual testament to the power of gravity within a compact galaxy group. Over millions of years, these galaxies will continue to evolve, and some may eventually merge into one massive galaxy, while others may be flung out of the group entirely, adding a dynamic element to the group's evolution. Interestingly, the interactions within these compact groups are not just limited to gravitational forces. Gas dynamics play a crucial role as well. Galaxies in these environments often have large amounts of intergalactic gas, which provides a unique backdrop for star formation. However, this gas is not always a passive observer. In some cases, the gas is pushed out of galaxies due to the force of an interaction. This phenomenon, known as ram pressure stripping, can lead to dramatic changes in the galaxies. The gas is literally stripped away as the galaxy moves through the hot, ionized medium that exists between galaxies. The process halts star formation and slowly depletes the galaxy's ability to generate new stars. In some cases, the gas can be stripped so completely that the galaxy is transformed into a red-ended elliptical galaxy, no longer able to form stars. In other instances, the gas can be compressed as galaxies collide, triggering a starburst. Starbursts are incredibly intense periods of star formation that occur when the gas in a galaxy is compressed, either through collisions or tidal forces. During a starburst, a galaxy can form a large number of stars in a relatively short period of time. This process can lead to the creation of massive stars, stellar clusters, and sometimes even a supermassive black hole in the galaxy's center. While starbursts can be a sign of intense activity within a galaxy, they are often short-lived events in the cosmic timescale, and once the gas is exhausted, the galaxy returns to a quieter state, with star formation significantly slowing down. The complex interplay between gravitational forces, gas dynamics, and dark matter within compact galaxy groups doesn't just influence the galaxy's structure and star formation, it also plays a role in the larger-scale cosmic evolution. The study of compact groups helps astronomers understand the processes that govern galaxy clusters, the massive structures that form when hundreds or even thousands of galaxies come together. Compact galaxy groups are essentially smaller versions of galaxy clusters, providing insights into how these larger systems might evolve over time. One of the key aspects of galaxy cluster formation is the idea of accretion, the process by which smaller groups of galaxies merge to form larger structures. Compact galaxy groups serve as the ideal setting to study this process on a smaller scale. As these groups interact, they merge and grow, eventually contributing to the larger-scale structures of the universe. This process is not a simple one, as it involves many factors, including dark matter, gas dynamics, and the gravitational pull of neighboring galaxies. The study of compact groups provides valuable information on how galaxies come together to form these massive clusters and how these clusters evolve over billions of years. While the study of compact galaxy groups provides a wealth of information, it is important to note that these systems are not static. They are constantly evolving, with galaxies moving in and out of the group, and interactions shaping the fate of each galaxy. As compact groups evolve, they may eventually merge into larger systems, or they may break apart as individual galaxies are ejected. This fluidity is part of what makes the study of compact galaxy groups so fascinating. These systems offer a glimpse into the forces that shape the universe on the largest scales, and by studying their evolution, we can better understand the underlying mechanisms that govern galaxy formation and evolution. The next frontier in the study of compact galaxy groups lies in the use of advanced observational techniques. With the advent of new telescopes and observatories, such as the James Webb Space Telescope and the upcoming Extremely Large Telescope, astronomers will be able to study these systems in unprecedented detail. These tools will allow for the observation of galaxies and their interactions across a wide range of wavelengths, from radio waves to X-rays. This multi-wavelength approach will provide a more comprehensive understanding of the processes at work within compact galaxy groups, from the behavior of dark matter to the interactions between galaxies and their gas. In addition to advanced observational tools, computational simulations will continue to play a critical role in our understanding of these systems. By creating detailed models of compact galaxy groups, astronomers can simulate the interactions and evolution of these systems over cosmic timescales. These simulations allow researchers to test hypotheses and refine our understanding of the complex dynamics at play. With more powerful computers and better simulation techniques, we will continue to gain deeper insights into the formation and evolution of galaxy groups and clusters. Another exciting development is the growing interest in the study of galaxy groups at different redshifts, essentially, observing these systems at various points in time. By studying compact galaxy groups at different redshifts, astronomers can track their evolution over billions of years. This will provide a clearer picture of how compact groups form, evolve, and eventually contribute to the larger-scale structures of the universe. Observing these systems at different points in time will allow us to better understand the processes that govern the birth and death of galaxies, as well as the role of dark matter and gas in shaping their evolution. The study of compact galaxy groups provides an invaluable window into the forces that shape the cosmos. These dense systems, with their intricate gravitational interactions, gas dynamics, and dark matter influence, serve as key players in the ongoing process of cosmic evolution. By studying these systems, we gain a deeper understanding of how galaxies form, interact, and evolve over time, shedding light on the processes that have shaped the universe as we know it. As we continue to explore these systems with more advanced observational tools and computational techniques, we will uncover even more secrets about the universe's complex and ever-changing nature. The ongoing exploration of compact galaxy groups reveals the immense complexity of the universe's fabric. The deep interaction between galaxies, the gas within them, and the dark matter that surrounds them challenges the way we have traditionally thought about the universe. Each compact galaxy group serves as a microcosm of larger cosmic processes, illustrating how even the smallest of structures can have profound implications for the evolution of the universe on grander scales. An intriguing aspect of compact galaxy groups is the possibility of multiple mergers occurring over billions of years. As smaller galaxies interact with each other, they can be pulled together by the immense gravitational forces at play, resulting in galactic mergers. These mergers are not merely cosmetic events. They often lead to the transformation of the merging galaxies into new and unique structures. A galaxy that undergoes multiple mergers might lose its spiral shape, transforming into an elliptical galaxy that is much more compact and lacks the distinctive structure of its original form. These mergers also result in the exchange of gas and stars between the galaxies involved, potentially sparking new waves of star formation and altering the stellar population of the newly merged galaxy. The effects of these mergers ripple through the entire compact group, influencing the dynamics of other galaxies within the group and even leading to the expulsion of galaxies that no longer fit within the evolving structure. The influence of supermassive black holes, SMBHs, also cannot be ignored when studying these galaxy groups. Almost every large galaxy, particularly those in compact groups, harbors a supermassive black hole at its center. These black holes are millions to billions of times the mass of the Sun, and are known to play a key role in the evolution of their host galaxies. In compact galaxy groups, interactions between galaxies can lead to the merging of these supermassive black holes. When this happens, it can result in the emission of powerful gravitational waves, as the newly merged black holes send ripples through spacetime. The collision of supermassive black holes is one of the most extreme events in the universe, and the detection of gravitational waves from such mergers could provide astronomers with valuable insights into the workings of these enigmatic objects. In addition to galactic mergers and supermassive black hole interactions, the gas within compact galaxy groups plays a pivotal role in shaping the galaxy's evolution. In these dense environments, the gas that exists between galaxies, known as the intergroup medium, can be subjected to significant pressure from the galaxy's motion. This pressure can result in the stripping of gas from the galaxies, as we discussed earlier, but it can also lead to the formation of new structures within the group. For example, the gas can become concentrated in certain areas, creating regions of high density where star formation can occur at an accelerated rate. These regions, known as star-forming knots, can be incredibly rich in young stars and are often seen as bright, energetic features within the group. The amount of gas present within a compact galaxy group also has a profound effect on the group's ability to form new galaxies. If the gas is abundant and dense enough, it can trigger the formation of new galaxies from the surrounding gas. This process is known as galaxy formation by gas condensation. In essence, the gas within the group clumps together, eventually collapsing to form new galaxies. This phenomenon is thought to have occurred in the early stages of the universe, when gas was more abundant, and is still an important process in some compact groups today. The intricate balance between the galaxy's gravitational interactions, the behavior of gas, and the presence of dark matter creates a delicate environment in compact galaxy groups. These groups are in a constant state of flux, with galaxies continually interacting, merging, and evolving. Over time, the dynamics within these groups will continue to shape the galaxy's structures and behavior. Some galaxies will eventually be ejected from the group entirely, while others may become central members of the group's evolving structure. This fluidity makes compact galaxy groups a particularly fascinating subject for study, as they offer a snapshot of the universe's ongoing process of evolution. In the context of the larger universe, compact galaxy groups also serve as laboratories for studying galaxy clusters. These groups are essentially smaller versions of galaxy clusters, and by studying them, astronomers can gain insights into how clusters evolve over time. As galaxy groups merge to form larger clusters, the dynamics of the group will evolve, and the galaxies within it will continue to interact, often resulting in the formation of even larger galaxies and more complex structures. An important factor that astronomers must consider when studying compact galaxy groups is the role of dark matter. Dark matter, which accounts for about 27% of the universe's total mass, exerts a gravitational influence on galaxies and groups of galaxies. It cannot be observed directly, but its presence is inferred from the gravitational effects it has on visible matter. In compact galaxy groups, dark matter contributes to the overall gravitational pull that governs the movement of galaxies. Understanding the distribution of dark matter within these groups is crucial for understanding their evolution, as it influences the way galaxies move and interact with one another. One of the most intriguing aspects of dark matter in compact galaxy groups is the possibility that it could play a role in the formation of galactic halos. These halos are vast regions of dark matter that surround galaxies and help to bind them together. The presence of dark matter in a compact group can create a shared halo that spans the entire group, influencing the behavior of the galaxies within it. By studying the distribution of dark matter in these groups, astronomers can gain valuable insights into the role dark matter plays in the formation and evolution of galaxies. The interaction between dark matter and visible matter also leads to fascinating phenomena such as gravitational lensing. This occurs when the gravitational field of a large galaxy or galaxy group bends the light from more distant objects, such as background galaxies. The result is the distortion of the image of the background object, creating an effect known as gravitational lensing. By studying this effect, astronomers can map the distribution of dark matter within galaxy groups and gain a better understanding of how dark matter interacts with visible matter. Gravitational lensing is not only a useful tool for studying galaxy groups, but it also provides a powerful way to probe the large-scale structure of the universe. Another emerging area of interest in the study of compact galaxy groups is the role of active galactic nuclei, AGNs. AGNs are incredibly energetic regions found at the centers of some galaxies, where supermassive black holes are actively accreting matter. As the material falls into the black hole, it heats up and emits vast amounts of radiation, which can outshine the entire galaxy. AGNs are thought to play a significant role in the evolution of their host galaxies, as the energy released during accretion can have a profound impact on the surrounding environment. In compact galaxy groups, where interactions between galaxies are frequent, AGNs may influence the evolution of nearby galaxies by regulating star formation and expelling gas. The study of AGNs in these environments could provide valuable insights into the feedback mechanisms that govern the evolution of galaxies. As we look ahead, the study of compact galaxy groups continues to be one of the most exciting areas in astrophysics. With advances in observational technology and computational simulations, we are on the cusp of uncovering even more mysteries about these enigmatic structures. The next few decades will likely bring about new discoveries that will deepen our understanding of how galaxies form, evolve, and interact with one another. By studying the smallest groups of galaxies, we are not only learning more about the universe on a small scale, but also gaining insights into the larger cosmic picture, helping us to unravel the mysteries of the cosmos one galaxy at a time. As we continue to explore the enigmatic nature of compact galaxy groups, it's essential to understand that these groups offer an invaluable perspective on the universe's larger-scale structures. The dense and tightly packed environment of compact galaxy groups provides astronomers with a living laboratory to examine the intricacies of galactic interactions, dark matter, gas dynamics, and cosmic evolution. Every new discovery in this domain adds a new layer to our comprehension of the cosmic dance between galaxies and their environments, leading us closer to unraveling the ultimate mysteries of the universe. At the core of these investigations lies the fundamental question: what drives the evolution of compact galaxy groups? As we study the interactions within these groups, we are confronted with the reality that these interactions are far from simple. They are driven by complex forces, ranging from gravitational interactions to the internal dynamics of each galaxy. One of the most intriguing aspects of compact galaxy groups is how they evolve over time. While some groups remain relatively stable, others experience dramatic transformations. Some groups may disperse over time, with galaxies being ejected, while others may collapse further, merging into even more compact structures. The evolution of these groups is not just a matter of the galaxies within them, but is intricately linked to the broader cosmic processes that influence all galaxies. A significant factor in this evolution is the interplay between the galaxy's internal dynamics and their interactions with the intergalactic medium. This medium is composed primarily of hot gas, which fills the space between galaxies and is heated to millions of degrees as a result of gravitational interactions. In compact galaxy groups, this intergalactic gas can be heated to such an extent that it forms a hot, diffuse plasma, which can influence the behavior of galaxies within the group. The hot gas can interact with the galaxies in several ways, including triggering the formation of new stars, stripping gas from the galaxies, and even altering the shape of the galaxies themselves. These interactions can lead to significant changes in the structure of the group and the galaxies within it. The role of galactic mergers in the evolution of compact galaxy groups is another fascinating aspect of these environments. As galaxies collide and merge, they undergo a series of dramatic changes. The gravitational forces involved in these mergers can cause the galaxies to lose their original structures, leading to the formation of elliptical galaxies that are much more compact than their progenitors. These mergers can also result in the creation of supermassive black holes, which can have a profound impact on the dynamics of the group. The energy released by these black holes during accretion can heat the surrounding gas, creating what is known as active galactic nuclei, AGN. AGNs are one of the most energetic phenomena in the universe, and their influence extends far beyond the galaxy in which they reside, affecting the entire group. One of the most remarkable features of compact galaxy groups is how they serve as microcosms for larger galaxy clusters. In many ways, the dynamics within compact groups mirror those of larger clusters, offering a glimpse into the future of galaxy clusters. By studying the interactions within compact groups, astronomers can better understand the processes that govern the formation and evolution of galaxy clusters. This knowledge can be used to refine our understanding of galaxy formation on a much larger scale and shed light on the complex role of dark matter, gas, and gravitational forces in shaping the cosmos. In addition to the fascinating internal dynamics of compact galaxy groups, the study of these groups has far-reaching implications for understanding the large-scale structure of the universe. As we explore these groups, we are simultaneously investigating the broader cosmic web in which they are embedded. Compact galaxy groups represent the small-scale components of the universe's large-scale structure, which consists of vast networks of galaxies, clusters, and filaments that stretch across billions of light-years. By studying the behavior of galaxies within these compact groups, we gain insights into the larger processes that shape the universe itself. Another intriguing aspect of compact galaxy groups is the role of dark matter in their evolution. Dark matter, which accounts for approximately 27% of the universe's total mass, exerts a powerful gravitational influence on galaxies and galaxy groups. However, unlike normal matter, dark matter does not emit, absorb, or reflect light, making it nearly invisible to traditional telescopes. Despite this, scientists have been able to detect dark matter through its gravitational effects on visible matter. In compact galaxy groups, dark matter plays a critical role in the gravitational binding of galaxies. The presence of dark matter in these groups helps to keep the galaxies bound together, preventing them from flying apart due to their mutual gravitational attraction. Understanding the distribution of dark matter within compact galaxy groups is essential for understanding the larger cosmic structure. The study of dark matter in these environments is particularly important because it allows astronomers to map the invisible mass that pervades the universe. By analyzing the motion of galaxies within compact groups and the way in which light from background objects is bent by the gravitational influence of dark matter, scientists can infer the distribution of dark matter within the group. This process, known as gravitational lensing, has become a powerful tool for studying the large-scale distribution of dark matter in the universe. In compact galaxy groups, the lensing effect can reveal the presence of dark matter halos that surround the galaxies, providing valuable insights into the structure of these mysterious objects. The study of the gas within compact galaxy groups is equally important for understanding their evolution. Gas plays a critical role in the dynamics of these groups, and its behavior can provide valuable clues about the group's history and future. The intragroup gas, which is the gas located between galaxies, is typically heated to millions of degrees as a result of the group's intense gravitational interactions. This hot gas can have a profound effect on the galaxies within the group, as it can strip away the gas from their outer regions, preventing new star formation. In some cases, the gas can be funneled toward the center of the group, where it can ignite new bursts of star formation. These processes are crucial for understanding how galaxy groups evolve and how new galaxies are formed within these environments. Furthermore, the presence of gas in compact galaxy groups can also influence the evolution of supermassive black holes. As gas falls toward the center of the group, it can feed the supermassive black holes at the centers of galaxies. This process, known as accretion, can generate enormous amounts of energy, which can be released in the form of radiation and high-energy particles. The energy released by these accreting black holes can have a significant impact on the surrounding environment, heating the intragroup gas and potentially preventing new stars from forming. The interplay between gas, dark matter, and supermassive black holes is a key factor in the evolution of compact galaxy groups. While compact galaxy groups are often viewed as smaller-scale analogs of galaxy clusters, they are also distinct in their own right. The high density of galaxies within these groups creates a unique environment in which galaxies can undergo intense interactions, mergers, and transformations. These interactions can lead to the creation of new structures, such as star-forming knots, as well as the transformation of existing galaxies into more compact, elliptical shapes. The study of these processes not only provides insight into the evolution of compact groups, but also offers a glimpse into the future of larger galaxy clusters. The evolution of galaxy groups, especially in the context of compact groups, is a dynamic and ongoing process. As galaxies interact with each other and with their environment, they undergo transformations that can change their structures, star formation rates, and even their fate within the larger cosmic web. In the coming decades, astronomers will continue to study compact galaxy groups, using advanced telescopes and simulations to uncover new insights into the complex interactions that govern the behavior of galaxies. The more we learn about these dense, tightly packed groups of galaxies, the more we are able to understand about the larger processes that shape the universe itself. Ultimately, the study of compact galaxy groups is a critical piece of the puzzle in our quest to understand the evolution of galaxies and the universe as a whole. These groups represent the extreme end of galactic interactions, where galaxies collide, merge, and evolve in ways that challenge our understanding of cosmic dynamics. By studying the intricate details of these compact structures, we are not only gaining insight into the forces that shape the universe, but also pushing the boundaries of our knowledge about the very nature of existence itself. As we continue our exploration of compact galaxy groups, we delve deeper into the individual processes that govern their evolution and their connection to the broader universe. These small yet dense collections of galaxies are far from static, and understanding their intricate dynamics reveals much about the larger forces that shape the cosmos. One of the central aspects of studying compact galaxy groups is understanding how their dense environments foster both the birth of new stars and the death of old ones. The dense environment within compact galaxy groups acts as a crucible for intense galactic interactions. These interactions are driven by the gravitational pull each galaxy exerts on the others, causing galaxies to collide, pass through one another, or merge. The resulting disturbances can trigger star formation in regions that were once quiescent. When galaxies collide, their gas clouds can compress, leading to the birth of new stars. This process, known as starburst activity, is particularly pronounced in compact galaxy groups. However, these interactions can also have the opposite effect. For example, during galaxy collisions, gas can be stripped from a galaxy, shutting down star formation and leaving the galaxy without the fuel it needs to create new stars. Over time, the galaxies within these groups may experience significant transformations, shifting from active, star-forming spirals to more passive, elliptical galaxies. The birth and death of stars within compact galaxy groups are often intertwined with the evolution of the supermassive black holes that reside at the centers of many of the galaxies within these groups. Supermassive black holes are believed to be fundamental components of galaxy formation and evolution. As gas falls toward a supermassive black hole, it heats up and emits vast amounts of radiation. This process, known as active galactic nuclei (AGN) activity, can influence the entire galaxy and the group as a whole. AGN activity can lead to feedback mechanisms that regulate the star formation rate within a galaxy, either enhancing it by providing additional energy and material for star formation or suppressing it by heating the surrounding gas and preventing it from collapsing to form new stars. One particularly fascinating aspect of compact galaxy groups is the way in which they offer insights into the role of black holes in the larger-scale structure of the universe. It's now believed that every massive galaxy harbors a supermassive black hole at its core, and the influence of these black holes extends far beyond the galaxies in which they reside. The energy and material released by AGN activity can influence the intragroup medium, heating it to such an extent that it suppresses star formation across the entire group. This feedback mechanism can regulate the growth of galaxies and even influence the formation of the larger cosmic structures that we see today. Understanding how these feedback processes work in compact galaxy groups gives us a window into the broader mechanisms at play in galaxy clusters and other large-scale structures. Beyond the effects of gravitational interactions and supermassive black holes, another crucial aspect of compact galaxy groups is the role of the intergalactic medium, IgM, the vast, diffuse gas that fills the space between galaxies. The IgM is composed primarily of hydrogen and helium gas, but it is also enriched with heavier elements such as carbon, oxygen, and nitrogen, which are produced through stellar processes. In the dense environments of compact galaxy groups, the IgM can play a vital role in shaping the evolution of the galaxies within the group. As galaxies interact, the hot gas within them can be stripped away, leading to a process known as ram pressure stripping. This process removes gas from the outer regions of galaxies, preventing further star formation. However, in some cases, the gas in the IgM can also be compressed or heated by interactions between galaxies, triggering the formation of new stars or even facilitating the growth of black holes. One key observation in the study of compact galaxy groups is the prevalence of what is known as the cannibalization process. This occurs when one galaxy within the group merges with or absorbs a smaller galaxy. Over time, this process can lead to the formation of more massive galaxies, particularly in the case of elliptical galaxies. The cannibalization process is not limited to individual galaxies, though. It can also involve the merging of entire galaxy groups. In the case of compact galaxy groups, this process can lead to the creation of more tightly bound structures, where galaxies lose their individuality and merge into a single, more massive entity. This merging process is one of the driving forces behind the evolution of the universe's largest structures, such as galaxy clusters. The role of dark matter in these processes is also critical. As we've discussed, dark matter is an invisible form of matter that interacts through gravity but does not emit or absorb light. It is thought to make up a significant portion of the mass in galaxy groups and clusters, and its gravitational influence can play a pivotal role in determining the dynamics of compact galaxy groups. The study of dark matter in these dense environments is ongoing, and scientists are using advanced techniques such as gravitational lensing to map its distribution within galaxy groups. Understanding the role of dark matter in shaping these groups is essential for understanding the overall structure of the universe. Another intriguing aspect of compact galaxy groups is their role in the larger process of cosmic evolution. These small but dense structures are like laboratories for studying the interactions that drive the growth and evolution of galaxies. By understanding how galaxies in compact groups evolve over time, scientists can better predict how galaxies in larger structures, such as galaxy clusters, will behave. The interactions within these groups serve as a microcosm for the broader forces that shape the universe. As compact galaxy groups continue to evolve, they provide crucial insights into the larger-scale processes that drive the formation and transformation of cosmic structures. Additionally, compact galaxy groups are also important for understanding the role of environment in the evolution of galaxies. In the early universe, galaxies were often found in isolation, and their evolution was driven primarily by internal processes such as star formation, mergers, and the growth of black holes. However, as the universe evolved, galaxies began to cluster together, and their evolution became increasingly influenced by external factors, such as the interactions within groups and clusters. The study of compact galaxy groups provides a glimpse into the early stages of this environmental influence, and helps to illuminate the role of galaxy groups in shaping the larger structures of the universe. Compact galaxy groups are not only important for understanding the evolution of galaxies but also for studying the broader cosmic web in which they are embedded. The universe is made up of a vast network of galaxies, clusters, and filaments that stretch across billions of light years. Compact galaxy groups are a crucial component of this web, as they represent the small-scale building blocks that eventually coalesce into larger structures. By studying the interactions within compact groups, scientists can gain insight into the processes that govern the formation of galaxies and clusters on a much larger scale. This knowledge can help refine our understanding of the universe's evolution and the forces that drive it. As we look to the future, the study of compact galaxy groups will continue to be a cornerstone of cosmological research. With the advent of more advanced telescopes and observational techniques, we are gaining unprecedented insights into the structure and dynamics of these groups. From the study of dark matter and gas to the investigation of galactic mergers and star formation, compact galaxy groups offer a wealth of knowledge that will shape our understanding of the universe for years to come. These dense, tightly packed environments hold the key to many of the most fundamental questions in cosmology, and each new discovery brings us one step closer to understanding the grand tapestry of the cosmos. The universe is vast, and there is still so much to learn. But as we continue to explore the mysteries of compact galaxy groups, we are unlocking secrets that will not only deepen our understanding of galaxy evolution but also bring us closer to unraveling the mysteries of the cosmos itself. Each new revelation about these groups brings us one step closer to answering the age-old question: how did the universe come to be, and what forces continue to shape its destiny? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.